The human mind has always been fascinated by time, its relentless forward march, its unyielding grip on our lives, and the tantalizing possibility of bending it to our will. For centuries, storytellers and philosophers have toyed with the idea of time travel, but none have captured its terrifying implications quite like the grandfather paradox. Imagine, for a moment, that you've discovered a way to traverse time. The machine hums softly as you input the coordinates. A small rural town in 1920. Your destination is precise. You're going to meet your grandfather as a young man, years before he would meet your grandmother. The controls are set, the countdown begins, and in a flash of light, you find yourself standing in a sun-dappled village square, watching a familiar figure walk by. Here's where the paradox takes hold. Suppose you raise a weapon. Suppose you pull the trigger. In that instant, you erase your own lineage. No grandfather means no parent, which means no you. But if you never existed, who pulled the trigger? How could the event have occurred at all? This is the grandfather paradox in its purest form, a self-contradictory loop that unravels the very fabric of causality. It's not merely a plot device for science fiction, it's a profound philosophical problem that forces us to question the nature of existence, the illusion of linear time, and the stability of reality itself. The grandfather paradox first emerged in early 20th century science fiction, but its roots stretch much deeper. Ancient myths and religious texts often grappled with the concept of predestination versus free will, the idea that our actions might be predetermined by forces beyond our control. The Greek tragedians wrote of heroes trying in vain to escape their fates, only to fulfill them through their attempts. In modern times, the paradox was crystallized in René Barjavel's 1943 novel Le Voyageur Imprudent, The Imprudent Traveler, where a time traveler kills his own ancestor, creating an impossible logical loop. Science fiction writers like Isaac Asimov and Robert Heinlein further popularized the concept, using it to explore the philosophical implications of time manipulation. But the paradox truly entered academic discourse when philosophers like David Lewis applied rigorous logical analysis to the problem. Lewis argued that time travel doesn't inherently create contradictions. It simply means that the time traveler's actions must be consistent with the timeline they came from. If you travel to the past, your presence there was always part of history. This idea, known as the consistency model, suggests that the universe has a way of preventing paradoxes from occurring. From a physics standpoint, the grandfather paradox intersects with some of the most cutting-edge theories in cosmology and quantum mechanics. Einstein's theory of general relativity allows for the theoretical possibility of closed time-like curves, paths through space-time that loop back on themselves, effectively permitting time travel to the past. However, most physicists agree that even if such time loops exist, nature likely has mechanisms to prevent paradoxes. One compelling idea is the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov in the 1980s. Novikov argued that any actions taken by a time traveler must align with the history they already know. In other words, the universe enforces consistency. You might try to kill your grandfather, but something will always prevent you from succeeding. Quantum mechanics offers another intriguing angle. The many worlds interpretation suggests that every possible outcome of an event spawns a new, branching universe. In this view, if you travel back and kill your grandfather, you don't erase your own existence. You simply create a new timeline where you were never born, while your original timeline remains intact. The grandfather paradox forces us to confront one of philosophy's oldest debates. Do we truly have free will, or are our actions predetermined? If time travel is possible and the past can be changed, it implies that our choices have real, causal power over reality. But if the universe self-corrects to prevent paradoxes, if every attempt to alter history is doomed to fail, then our sense of agency might be an illusion. We might be like actors in a play, reciting lines that were written long before we took the stage. This idea, known as determinism, suggests that all events are the inevitable result of prior causes. The 18th century philosopher Pierre-Simon Laplace imagined a hypothetical Laplacian demon that could know the position and momentum of every particle in the universe, and thus could compute the entire past and future with perfect accuracy. In such a universe, Time travel wouldn't create paradoxes because every action would already be accounted for in the grand equation of reality. But if determinism is true, what does that mean for concepts like morality, responsibility, and personal identity? If we can't truly choose differently, can we be held accountable for our actions? To further explore the paradox, let's consider some variations. 1. The Hitler assassination paradox. What if, instead of targeting your grandfather, you traveled back to kill a historical tyrant like Adolf Hitler? At first glance, this seems like an unambiguous good, but the implications are equally troubling. If Hitler dies young, World War II might never happen, which could mean the post-war geopolitical landscape changes drastically. Perhaps the Cold War escalates into nuclear conflict, or technological progress stagnates without the pressures of war. The point is, even well-intentioned changes to the past could have catastrophic ripple effects. 2. The self-fulfilling paradox. Imagine traveling back to give your younger self a critical piece of advice. But what if that advice only makes sense because you received it from your future self? This creates a loop where the cause and effect are indistinguishable. The information has no origin point. 3. The information paradox. A variation involves knowledge rather than physical actions. Suppose a time traveler brings back a Shakespearean play to the past and publishes it under their own name. Shakespeare then never writes it in the original timeline. Where did the play come from? Each of these scenarios deepens the mystery of causality and challenges our understanding of time as a linear, one-way progression. Beyond the physics and philosophy, the grandfather paradox taps into something deeply unsettling about human psychology, the fear of erasure, of being rendered inconsequential. If our existence is so fragile that a single altered event could undo it, how do we find meaning in our lives? This existential anxiety mirrors questions raised by nihilism and absurdism, philosophies that grapple with the apparent meaninglessness of the universe. At the same time, the paradox invites us to reflect on the nature of identity. If you could go back and change your past, would you still be you? Or would you become someone entirely different, a product of a new timeline? The grandfather paradox leaves us with more questions than answers, but that's the beauty of philosophical inquiry. It reminds us that reality might be far stranger than we imagine, a web of cause and effect that doesn't always follow the rules we expect. And if time itself is this malleable, what does that say about the things we consider unchanging, like our own identities? Which brings us to our next exploration, the Ship of Theseus, a paradox that challenges the very notion of what it means to persist over time. Imagine standing before an ancient Greek warship, its wooden planks weathered by centuries of ocean voyages. This is the Ship of Theseus, the legendary vessel that carried the mythical king home from Crete after he slew the Minotaur. Over time, as the ship's planks rot, each one is carefully replaced until, eventually, not a single original piece remains. Here lies the paradox. Is this still the Ship of Theseus? If not, at what point did it cease to be the same ship? And more unsettling, if all the original planks were gathered and reassembled into a ship, which one would be the true Ship of Theseus? This ancient thought experiment, first recorded by Plutarch, doesn't just challenge our notions about objects, it forces us to confront fundamental questions about identity, continuity, and the nature of the self. If every cell in our body regenerates over time, are we still the same person we were a decade ago? Or are we, like the ship, just a collection of parts pretending to be a whole? The Ship of Theseus paradox dates back to antiquity, but its implications have echoed through centuries of philosophical thought. The Greek historian Plutarch first posed the question in his work, Life of Theseus, while later philosophers like Thomas Hobbes added a crucial twist. What if someone collected all the original discarded planks and rebuilt the ship? Which version would hold the true identity? In the 17th century, John Locke expanded this concept to personal identity in his essay concerning human understanding. Locke proposed that consciousness, not physical continuity, defines the self, a revolutionary idea that still influences modern psychology and neuroscience. The paradox gained new life in the 20th century through analytic philosophers like W.V. Quine, who used it to explore problems of reference and identity in language. Modern science makes this ancient paradox even more perplexing. Biological studies reveal that nearly all the atoms in our bodies are replaced every 7 to 10 years. The stomach lining renews every 4 days, skin cells every month, and even our skeleton completely regenerates every decade. Quantum physics adds another layer. At the subatomic level, particles are constantly blinking in and out of existence. Neurologically, our brains undergo constant rewiring. Memories fade and reconstruct themselves each time we recall them, a phenomenon called reconsolidation. This means the very memories that form our identity are unstable, changing with each recollection. The implications are staggering. If both our physical and mental components are in constant flux, what remains to constitute a continuous self? Are we like rivers, appearing constant while the constituent waters are always changing? Philosophers have proposed several solutions to the paradox, each with profound implications. The endurantist view argues that objects persist through time by being wholly present at each moment. The ship remains the same because its essential form or shipness continues, regardless of material changes. This aligns with Aristotle's concept of formal cause, the idea that an object's identity comes from its structure and purpose rather than its materials. The perdurance theory suggests objects are four-dimensional, extending through time like a long worm. Each temporal slice of the ship is a different part of the whole, meaning the ship at time A and time B are different temporal parts of the same extended object. The stage theory takes this further, proposing that each moment presents a distinct stage of the object. The ship isn't identical across time but is connected by causal and similarity relations that create the illusion of continuity. Our intuitive understanding of identity reveals much about human cognition. Psychological studies show we rely on narrative continuity to maintain our sense of self. We construct life stories that connect our past, present, and future selves, creating an illusion of stability despite constant change. This explains why we might view childhood photos and say, "That's me," despite having no physical or mental continuity with that child. Memory plays a crucial role. Patients with severe amnesia often lose their sense of personal identity, suggesting our self-conception depends on psychological continuity more than physical continuity. The paradox also manifests in modern dilemmas. Consider the triggers broom concept from British comedy. A character claims to have used the same broom for 20 years, despite replacing both the head and handle multiple times. This mirrors contemporary questions about heritage restoration. When does repair become replacement? At what point does the Notre Dame Cathedral, after reconstruction, cease to be the original medieval structure? The Ship of Theseus takes on new urgency in our age of advanced prosthetics and potential mind uploading. If a person gradually replaces body parts with synthetic alternatives, at what point do they stop being human? If we could scan and upload a human consciousness to a computer, would the digital version be the same person? These questions aren't just theoretical. Neural implants are already being tested to restore brain function, while companies work toward whole brain emulation. The paradox forces us to confront what truly constitutes human identity in an era where the boundaries between organic and artificial, physical and digital, are blurring. The paradox has inspired countless artistic explorations. Jorge Luis Borges' short story, Theseus Ship, reimagines the paradox through literary lenses. The 2012 film, Cloud Atlas, presents a thematic exploration of identity across time and changing forms. Even popular culture references the concept. In Doctor Who, the TARDIS undergoes complete internal redesigns while remaining the same ship. These artistic interpretations highlight how the paradox resonates with fundamental human concerns about mortality, legacy, and the nature of existence. They remind us that identity is as much about perception and story as it is about physical continuity. The Ship of Theseus leaves us questioning not just objects, but our very selves. If identity is so fluid, how can we trust our perceptions of reality? This uncertainty leads us to our next exploration, the brain in a vat, a thought experiment that challenges whether we can know anything about the world beyond our own minds. The year is 2157. You awaken in a sterile white room, your body connected to an intricate network of tubes and wires. A scientist in a lab coat approaches and delivers the devastating news. Your body perished in an accident years ago. We saved your brain, keeping it alive in this nutrient solution while connecting it to a perfect virtual reality simulation. As you reel from this revelation, the scientist adds the final twist. How do you know this isn't happening right now? This is the essence of the brain in a vat thought experiment, one of philosophy's most radical challenges to our perception of reality. First formulated in modern philosophy by Hilary Putnam, though with roots stretching back to Descartes' evil demon, this hypothesis suggests that everything you experience, the warmth of sunlight, the touch of a loved one, even the device you're using to watch this video, could be nothing more than electrical signals fed to a disembodied brain floating in a vat of nutrients. The implications are staggering. If we can't prove we're not brains in vats, how can we claim to know anything about the real world? This dilemma doesn't just belong to philosophers, it's been explored by neuroscientists studying perception, by computer scientists developing virtual reality, and even by filmmakers creating stories about simulated worlds. The concept of radical skepticism about reality has ancient origins. In the 4th century BC, the Chinese philosopher Zhuangzi dreamed he was a butterfly, then awoke uncertain whether he was Zhuangzi who had dreamed of being a butterfly, or a butterfly now dreaming he was Zhuangzi. This poetic metaphor captures the same fundamental uncertainty about the nature of experience. René Descartes, in his 1641 Meditations on First Philosophy, introduced the modern version of this worry with his evil demon hypothesis, the idea that an all-powerful malicious being could be systematically deceiving us about all our experiences. Descartes used this radical doubt as a tool to find indubitable foundations for knowledge, ultimately arriving at cogito, ergo sum, I think, therefore I am. The contemporary brain in a vat version gained prominence through Hilary Putnam's 1981 book Reason, Truth and History, where he used it to explore questions about meaning, reference, and the relationship between minds and worlds. Interestingly, Putnam ultimately argued that the scenario might be self-refuting, a position we'll examine in depth later in this segment. Modern neuroscience makes the brain in a vat scenario more plausible than ever before. We now know that all our experience of reality is mediated by the brain's interpretation of sensory inputs. The visual cortex constructs our experience of sight from electrical impulses traveling along the optic nerve. Damage to specific brain areas can radically alter perception. Patients with Charles Bonnet syndrome see vivid hallucinations, while those with Capgras delusion believe their loved ones have been replaced by imposters. Experiments with sensory deprivation and altered input reveal how plastic our perception of reality truly is. In the 1950s, psychologist Donald Hebb paid McGill University students to stay in soundproof, light-diffusing rooms with only minimal sensory input. Within hours, participants began experiencing vivid hallucinations and extreme disorientation. More recently, virtual reality systems have demonstrated how easily the brain can be tricked into accepting artificial environments as real, a phenomenon called presence in VR research. The rubber hand illusion provides another striking example. When researchers stroke a visible rubber hand while simultaneously stroking a participant's hidden real hand, the brain quickly begins to accept the fake hand as part of the body. Such experiments demonstrate that our sense of embodiment, the feeling that we inhabit our physical forms, is more fragile than we might assume. Philosophers have developed several responses to the brain in a vat scenario. 1. Putnam's self-refutation argument. Hilary Putnam famously argued that if we were brains in vats, we couldn't coherently think or say that we were. His reasoning hinges on theories of reference and meaning. The words brain and vat in the vat world would refer to virtual brains and vats, not real ones, making the statement, "I am a brain in a vat," false when uttered by a vat brain. 2. Phenomenological approaches. Following Husserl and Merleau-Ponty, some philosophers argue that the lived experience of embodiment provides its own validation. The way we experience gravity, resistance, and the limitations of our bodies suggests a reality that transcends mere simulation. 3. Inference to the best explanation. Many philosophers follow this common-sense approach. While we can't absolutely disprove the brain in a vat hypothesis, the ordinary explanation that our perceptions reflect reality is far simpler and better supported than the elaborate deception scenario. 4. The problem of other minds. Some argue that the brain in a vat scenario merely amplifies the fundamental problem of solipsism. How can we know other minds exist at all? Most philosophers consider this an unproductive line of inquiry that leads to philosophical paralysis. The brain in a vat thought experiment has taken on new urgency with recent technological developments. 1. Virtual reality advancements. As VR systems achieve greater sensory fidelity, the line between virtual and physical reality blurs. Neural interface technologies could eventually bypass sensory organs entirely, feeding signals directly to the brain. 2. Brain-computer interfaces. Companies like Neuralink are developing direct neural connections between brains and computers. While currently aimed at medical applications, the long-term possibilities raise profound questions about the nature of experience. 3. Whole brain emulation. The theoretical possibility of scanning and simulating an entire human brain in a computer brings the brain in a vat scenario closer to potential reality. Philosophers like Nick Bostrom have argued we might already be living in such simulations. 4. The simulation argument. Building on the brain in a vat idea, Bostrom's simulation hypothesis suggests that advanced civilizations might create countless simulated realities, making it statistically likely we're in one. This modern version has gained surprising traction among technologists and philosophers alike. Contemplating the brain in a vat scenario can induce what philosophers call existential vertigo, a dizzying sense of disconnection from reality. This mirrors clinical conditions like derealization disorder, where patients feel persistently detached from their surroundings. However, psychologists note that healthy individuals typically maintain what's called naive realism, the unshaken conviction that our perceptions reflect objective reality. This may be an evolutionary adaptation. Organisms that spent too much time doubting reality's existence would be less successful than those that took their senses at face value. The scenario also raises questions about the nature of suffering and meaning. If all our experiences were simulations, would our joys and sorrows be less real? This echoes age-old philosophical debates about the reality of subjective experience versus objective reality. The brain in a vat hypothesis has permeated popular culture, appearing in numerous films, books, and television shows. The Matrix, 1999, brought the concept to mass audiences with its depiction of humans unknowingly living in a simulated reality. Total Recall, both 1990 and 2012 versions, explores similar themes of implanted memories and uncertain realities. Black Mirror episodes like Playtest and USS Callister examine modern technological takes on the concept. Philosopher Jean Baudrillard's theories of hyperreality, which influence The Matrix, argue we increasingly live in a world of simulations detached from any original reality. These cultural artifacts demonstrate how the philosophical thought experiment resonates with fundamental human anxieties about authenticity, identity, and the nature of existence. The brain in a vat scenario leaves us with profound uncertainty about the nature of reality. But if we can't be sure about external reality, perhaps we can at least be certain of our own thoughts and experiences. Or can we? This brings us to our next exploration, the problem of other minds. How can we know that other people are truly conscious beings like ourselves, and not just sophisticated philosophical zombies going through the motions of consciousness? You're sitting in a crowded cafe, surrounded by the murmur of conversation. The barista smiles as she hands you your coffee. A couple argues quietly in the corner. A student highlights passages in a textbook. All around you, people appear to be having rich inner experiences just like your own. But here's the unsettling question. How can you be certain? This is the problem of other minds, one of philosophy's most persistent and unsettling puzzles. While you have direct access to your own thoughts, feelings, and sensations, you can never directly experience another person's consciousness. For all you know, everyone around you could be sophisticated philosophical zombies, entities that behave exactly like conscious beings but lack any inner experience whatsoever. The implications are profound. If we can't prove other minds exist, How can we justify our moral systems that depend on recognizing others' suffering? How can we trust our social bonds? This problem doesn't just belong to abstract philosophy, it emerges in artificial intelligence research, clinical psychology, and even our everyday relationships. The problem has roots in Descartes' mind-body dualism, which separated the mental and physical into distinct substances. While Descartes believed other humans had minds like his own, arguing from analogy with his own behavior, he couldn't prove it with his rigorous standards of certainty. John Stuart Mill later formulated the classic argument from analogy. Since other people's bodies and behaviors resemble our own, we can reasonably infer they have similar mental states. But this reasoning contains a gap. Analogies work when we can verify both sides, but with other minds, we can only observe behavior, never the consciousness itself. In the 20th century, Ludwig Wittgenstein's private language argument challenged traditional approaches. He suggested that our very concept of mental states depends on public, observable criteria, meaning the inner and outer might not be as separate as we imagine. Behaviorists like B.F. Skinner took this further, arguing that we should dispense with talk of inner states altogether and focus solely on observable behavior, a position now largely rejected but which influenced psychology for decades. Modern neuroscience reveals both the promise and limitations of solving the problem empirically. 1. Mirror neuron systems. Discovered in the 1990s, these brain cells fire both when we perform actions and when we observe others performing them, potentially providing a neural basis for empathy and understanding others' intentions. 2. Theory of mind. Developmental psychology shows that children develop the ability to attribute mental states to others around age 4, tested through false belief tasks, suggesting this capacity is fundamental to human cognition. 3. Brain synchronization studies. fMRI research demonstrates that people's brains show similar activation patterns when sharing experiences, watching the same movies, or conversing, hinting at possible objective markers of shared subjective states. 4. Disorders of social cognition. Conditions like autism spectrum disorder, where interpreting others' mental states can be challenging, and Capgras delusion, where familiar people are believed to be imposters, reveal how fragile our mind-reading abilities can be. Yet these scientific approaches still face the fundamental gap. We can correlate neural activity with reported experiences, but we can never directly observe another's qualia, the felt quality of experiences like the redness of red or the pain of a headache. Philosophers have developed several approaches to the problem. 1. Solipsism, the radical position that only one's own mind is certain to exist. While logically irrefutable, most philosophers reject it as an unlivable and unproductive stance. 2. Inference to the best explanation, the common-sense view that other minds provide the best explanation for the complex, responsive behavior we observe in others. 3. Simulation theory, the idea that we understand others by mentally simulating their situations, supported by some neuroscientific evidence about mirror systems. 4. Phenomenological approaches. Philosophers like Husserl and Merleau-Ponty argue that we directly perceive others' mental states in their expressive behavior, not through inference. 5. The zombie argument. David Chalmers' philosophical zombies thought experiment suggests consciousness might be separate from physical processes, making other minds even more mysterious. The problem takes on new dimensions with AI development. Alan Turing proposed his famous test, 1950, where if a machine could converse indistinguishably from a human, we should consider it thinking. But this behavioral standard precisely mirrors the other mind's problem. Passing the test proves nothing about inner experience. Modern AI systems like large language models can produce remarkably human-like responses while arguably lacking any understanding or consciousness. This forces us to ask, if we can't be sure about other humans' consciousness, how could we ever be certain about machines? Some philosophers propose consciousness tests based on specific neural architectures or information integration measures, but these remain controversial. The hard problem of consciousness, Chalmers, suggests there may always be an unbridgeable explanatory gap between physical processes and subjective experience. The problem isn't just academic, it has real-world consequences. 1. Medical ethics. Determining consciousness in coma patients or those with locked-in syndrome involves interpreting ambiguous behavioral and neural signs. 2. Animal rights. If we accept that other species might have conscious experiences, even if different from ours, this affects how we treat them. 3. Social relationships. Our entire social fabric depends on assuming others have rich inner lives like our own. What would relationships mean if we truly doubted others' consciousness? 4. Artificial entities. As we create more sophisticated robots and virtual beings, we'll face increasing uncertainty about their moral status. The problem has inspired numerous artistic treatments. Philip K. Dick's works, like Do Androids Dream of Electric Sheep, explore what distinguishes human consciousness from artificial minds. Kazuo Ishiguro's Clara and the Sun examines an artificial being's capacity for love and understanding. Films like Ex Machina and Blade Runner dramatize the difficulty of detecting true consciousness behind convincing behavior. The Chinese Room thought experiment, Searle, became a cultural touchstone for debates about AI understanding. These works reflect our deep cultural anxiety about the opacity of other minds, whether human, animal, or artificial. The problem of other minds leaves us in profound isolation, unable to ever truly know another's inner experience. But perhaps there's an even more fundamental uncertainty: how can we be sure about our own minds? This brings us to our next paradox: the illusion of the self, the startling possibility that the you take for granted might not exist in the way you imagine. You wake up each morning with an unshakable certainty: you exist. The I that reads these words feels like the most undeniable reality. But what if this sense of self is the most sophisticated illusion your brain has ever created? Consider this moment. As you watch this video, you likely feel like a unified observer experiencing a continuous stream of consciousness. Yet neuroscience reveals a startling truth: your brain is actually processing different aspects of this experience. The sounds, the visuals, the meanings, in separate regions at slightly different times, and then stitching them together to create the illusion of a single, coherent experience. This is the paradox of selfhood. The you that feels so real may be more like a story your brain tells itself than an actual entity. From Buddhist philosophers who spoke of an atta, non-self, to modern neuroscientists who can't locate a self-center in the brain, the evidence mounts that our most fundamental sense of identity might be a beautifully constructed fiction. The questioning of selfhood has ancient roots across multiple traditions. 1. Buddhist philosophy, 5th century BC. The concept of an atta, Pali, or an Atman, Sanskrit, proposes that what we call the self is merely a temporary constellation of ever-changing physical and mental components, skandhas, lacking any permanent essence. 2. Hume's bundle theory. 18th century Scottish philosopher David Hume famously found no enduring self when he introspected, only a bundle or collection of different perceptions which succeed each other with an inconceivable rapidity. 3. Eastern mysticism. Advaita Vedanta Hinduism teaches that the individual self, jiva, is ultimately an illusion, maya, with only the universal Brahman being truly real. 4. Postmodern philosophy. Thinkers like Michel Foucault and Jacques Derrida challenged the notion of a coherent, autonomous self, viewing it instead as a social construction shaped by language and power structures. These diverse traditions converge on a radical idea: the solid, continuous I we experience may be more process than thing, more verb than noun. Modern brain research provides startling evidence for the illusory nature of the self. 1. The split brain phenomenon. Patients whose corpus callosum has been severed to treat epilepsy demonstrate that the brain can house two separate streams of consciousness that sometimes conflict, suggesting the unified self is a fragile construction. 2. Default mode network. This interconnected brain system activates during rest and self-referential thought. While often called the self network, its distributed nature shows selfhood emerges from coordinated activity, not a single center. 3. Out-of-body experiences. By electrically stimulating specific brain regions, like the temporoparietal junction, neuroscientists can induce profound alterations in self-perception, including the sense of floating outside one's body. 4. Thought timing experiments. Studies by Benjamin Libet and others show brain activity precedes conscious decisions by milliseconds, suggesting the self may rationalize actions after they're initiated rather than causing them. 5. Neuroplasticity cases. Patients who gradually lose brain regions through injury or disease often maintain an intact sense of self, demonstrating its remarkable adaptability and constructed nature. Philosophers have proposed various frameworks to explain what constitutes personal identity over time. 1. Psychological continuity theory. Locke identity depends on the continuity of memory and psychological traits rather than physical continuity. 2. Narrative self theory. Dennett, Schechtman. The self is a center of narrative gravity, a story we constantly tell ourselves to make sense of our experiences. 3. Process philosophy. Whitehead rejects static notions of selfhood entirely, viewing identity as an ever-changing process without fixed boundaries. 4. Eliminativism. Churchland argues that our folk psychological concepts like self and free will may need to be discarded as neuroscience advances, much like we discarded phlogiston theory. These theories all grapple with the same fundamental puzzle. If all the components of selfhood, body, memories, personality, can change while we still feel like ourselves, what exactly is this self we're referring to? Our everyday experience of selfhood involves several interacting systems. 1. Autobiographical self. The story we construct about who we are based on memories and projected futures. Damage to memory systems can profoundly disrupt this narrative. 2. Agentive self. The sense that we are the authors of our actions. Experiments show this can be easily manipulated. People will confidently claim authorship of actions they didn't actually perform. 3. Minimal self. The basic sense of I in the present moment. Even this can be disrupted in conditions like depersonalization disorder, where people feel detached from their own existence. 4. Social self. The versions of identity we construct in different social contexts, demonstrating how fluid self-presentation can be while still feeling authentic. Cognitive science reveals that our sense of unity is achieved through constant editing and selective attention, ignoring countless inconsistencies and changes that would otherwise shatter the illusion of coherence. Emerging technologies are creating new challenges to traditional notions of selfhood. 1. Digital selves. Our online personas develop semi-independent existences, raising questions about which version is the real us. 2. Mind uploading. Theoretical future technologies might copy a brain's contents into a computer. Would the digital version be you or a copy? 3. Augmented cognition. Brain-computer interfaces and neuroprosthetics are blurring the boundaries between biological and technological aspects of self. 4. Distributed consciousness. Some theorists speculate about network-based consciousness where identity could be spread across multiple nodes or bodies. These developments force us to confront whether selfhood is tied to biological continuity or can exist in other substrates. Recognizing the illusory nature of selfhood can have profound consequences. 1. Mental health. Some therapeutic approaches, like mindfulness, leverage self-illusion insights to reduce suffering by decreasing identification with transient thoughts and emotions. 2. Moral responsibility. If the self is less substantial than we thought, how does this affect concepts like accountability and justice? 3. Spiritual practices. Many contemplative traditions use self-inquiry to transcend limited ego identifications, potentially leading to what's described as more expansive states of being. 4. Daily life. Understanding the constructed nature of self can help us be more flexible in our identities and less attached to rigid self-concepts that cause suffering. The fluidity of self has inspired countless creative explorations. Fight Club, novel and film, dramatizes the fragmentation of identity through dissociative identity disorder. A Borges short story, Borges and I, explores the divide between the public and private self. Black Mirror episodes like White Christmas examine digital copies of consciousness. Contemporary art installations use technology to create experiences of self-dissolution or multiplicity. These works reflect our cultural fascination with and anxiety about the instability of identity in an increasingly complex world. Having deconstructed the notion of an enduring self, we're left with a profound question. If the I is an illusion, what's doing the experiencing? This brings us to our next exploration, the hard problem of consciousness. Why does any experience exist at all, and how does subjective awareness emerge from physical processes? Imagine standing on a beach at dusk, feeling the cool sand between your toes, watching the waves dissolve into foam as they meet the shore. The salt air fills your lungs, and for a moment, you're overcome with a profound sense of wonder, not just at the scene before you, but at the miraculous fact that you're here to experience it at all. This simple moment contains philosophy's greatest unsolved mystery. Why should any of this feel like anything? Why doesn't the universe just hum along in the dark, an endless cascade of cause and effect with no one to witness it? This is the hard problem of consciousness, a phrase coined by philosopher David Chalmers in 1995 to distinguish between what he called the easy problems of consciousness, explaining cognitive functions like attention or memory, and the truly hard problem, why and how physical processes in the brain give rise to subjective experience. It's the difference between explaining how the visual system processes wavelengths of light and explaining why we experience the vibrant redness of a rose or the deep blue of the twilight sky. The problem runs so deep that some philosophers believe we might need to revolutionize our entire understanding of reality to solve it. The mystery of consciousness has haunted thinkers for millennia. Ancient Hindu scriptures from the Upanishads grappled with the relationship between the observing self and the physical world, proposing that consciousness might be more fundamental than matter. Greek philosophers like Plato envisioned the soul as an immaterial essence temporarily housed in the body, while Aristotle saw the mind as the form of the body, inseparable yet somehow more than just physical. The modern formulation of the problem began with René Descartes in the 17th century, whose famous cogito ergo sum, I think therefore I am, placed conscious experience at the foundation of all knowledge. Descartes' dualism divided reality into thinking substance and extended substance, but this created the notorious mind-body problem. How could these two fundamentally different substances interact? As science progressed through the Enlightenment and into the modern era, materialist explanations seemed to explain more and more of human cognition and behavior. Yet the essential mystery remained untouched. Gottfried Leibniz captured this perfectly with his thought experiment about walking through an imaginary brain mill. Even if we could see every cog and wheel of the brain's machinery turning, he argued, we would never find consciousness itself among the moving parts. The 20th century saw various attempts to explain consciousness in purely physical terms, from behaviorism's dismissal of inner experience to identity theory's claim that mental states simply are brain states. But none could bridge what philosopher Joseph Levine called the explanatory gap, the chasm between our physical descriptions of brain processes and the vivid reality of what it feels like to be conscious. Modern neuroscience has made extraordinary progress in identifying what's called the neural correlates of consciousness, the specific brain processes that accompany conscious experience. Researchers have discovered that certain patterns of synchronized neural activity, particularly in the thalamocortical system, reliably appear when subjects report being conscious of a stimulus. The global workspace theory suggests that consciousness arises when information is broadcast widely across the brain, while integrated information theory proposes that consciousness corresponds to a system's capacity to integrate information in a unified way. Cutting-edge experiments using psychedelics, meditation, and advanced brain imaging have revealed how altering brain function can dramatically transform conscious experience. We've learned that stimulating specific brain areas can induce out-of-body experiences or vivid memories, while damage to other areas can eliminate awareness of entire categories of objects while leaving basic vision intact. Yet for all these advances, the hard problem remains stubbornly resistant. Knowing which neurons fire when someone experiences pain doesn't explain why pain feels painful. Understanding how the visual system processes color doesn't explain why red looks red rather than blue. The neuroscientist's map of brain activity, no matter how detailed, always seems to leave out the essential feature, the experience itself. Faced with this persistent mystery, philosophers have developed several major approaches. Dualists maintain that consciousness is fundamentally non-physical, though they differ on how this mental substance relates to the physical world. Property dualists suggest that consciousness is an irreducible property that emerges from certain complex physical systems, much like wetness emerges from water molecules without being reducible to them. Physicalists argue that consciousness must be explainable in physical terms, though they disagree about how this might work. Some propose that we simply need better neuroscientific concepts, while others suggest that consciousness might be a fundamental property of matter, appearing only in certain complex arrangements. This latter view shades into panpsychism, the idea that some rudimentary form of experience exists even at the most basic levels of reality. At the more radical end, illusionists argue that the hard problem arises from a mistaken intuition, that the vivid sense we have of rich inner experience is itself a kind of illusion created by the brain's storytelling mechanisms. Meanwhile, Mysterians suggest that the hard problem might simply be beyond human cognitive capacities to solve, just as quantum physics is beyond the comprehension of a chimpanzee. The search for a solution to the hard problem has led researchers into some fascinating territory. Quantum consciousness theories, like those proposed by Roger Penrose and Stuart Hameroff, suggest that quantum processes in microtubules within brain cells might explain the unity and non-computational aspects of consciousness, though these ideas remain controversial. Other scientists are exploring how information processing might give rise to experience. Giulio Tononi's integrated information theory attempts to mathematically quantify consciousness by measuring how much a system's informational states depend on each other. While promising, even its proponents admit it doesn't fully explain why integrated information should feel like anything. Meanwhile, studies of altered states of consciousness, from meditation to psychedelics to near-death experiences, continue to reveal how flexible and surprising conscious experience can be. Research on patients with split brains or various forms of brain damage shows that our normal sense of unified consciousness is more fragile than we might assume. The hard problem isn't just an abstract philosophical puzzle, it has profound implications across many fields. In artificial intelligence, it raises the question of whether we could ever create a machine that's truly conscious and how we would know if we had. In medicine, it complicates decisions about patients in vegetative states or with locked-in syndrome. In animal ethics, it challenges us to determine which creatures might be conscious and what moral consideration they deserve. The legal system assumes conscious intention behind actions, but what does this mean if we can't properly define consciousness? Our understanding of mental illness depends on assumptions about normal conscious experience. Even physics faces questions about whether consciousness plays some fundamental role in reality, as suggested by interpretations of quantum mechanics that place observation at the center of physical reality. Artists and writers have long grappled with the mystery of consciousness. Jorge Luis Borges' short stories often play with the boundaries between perception and reality. Films like The Matrix and Inception explore how subjective experience might be constructed or manipulated. Contemporary artists like James Turrell create installations that highlight the active role consciousness plays in constructing visual experience. In literature, stream of consciousness techniques pioneered by writers like Virginia Woolf and James Joyce attempt to capture the fluid, subjective nature of experience. Science fiction authors from Philip K. Dick to Ted Chiang have used imagined forms of consciousness to explore what it means to be aware, to remember, to experience. These cultural reflections remind us that the hard problem isn't just academic, it's intimately connected to how we understand ourselves, create meaning, and relate to each other and the world around us. As we contemplate the mystery of consciousness, we inevitably wonder about its persistence beyond our physical existence. This leads us to our next profound question. If consciousness exists, could it survive the death of the body? Our next exploration takes us into the afterlife paradox, where we'll examine the philosophical puzzles surrounding concepts of life after death and what they reveal about the nature of consciousness itself. As night falls and the world grows quiet, a question as old as human thought itself emerges from the shadows. What happens to us when we die? Across cultures and centuries, humanity has woven elaborate tapestries of belief about existence beyond physical death, from the Egyptian Book of the Dead to modern near-death experience accounts. Yet beneath these varied visions lies a profound philosophical puzzle. How could consciousness, which appears so intimately tied to the living brain, possibly persist when the body has returned to dust? This is the afterlife paradox, the collision between our deep yearning for continuity and the cold logic of biology. We can imagine an afterlife, but can such a concept withstand rational scrutiny? The question forces us to confront fundamental mysteries about the nature of consciousness, identity, and the very fabric of reality. Whether we approach it through philosophy, neuroscience, or physics, the afterlife hypothesis presents us with a series of mind-bending contradictions that challenge our most basic assumptions about existence. The human preoccupation with life after death stretches back to our earliest records. Neanderthal burial sites from 100,000 years ago show careful placement of bodies with grave goods, suggesting beliefs in some form of continued existence. Ancient Egyptian civilization devoted enormous resources to preparing for the afterlife, developing complex theories about multiple soul components and their post-mortem journeys. The Babylonian epic of Gilgamesh, one of humanity's oldest written stories, grapples with the hero's desperate search for immortality after witnessing his friend's death. Greek philosophy offered more abstract conceptions, with Plato's theory of the immortal soul influencing later Western thought, while Eastern traditions developed sophisticated models like the Buddhist concept of rebirth without a permanent self. The Abrahamic religions introduced judgment-based afterlives where eternal fates hinged on earthly actions. What's striking across all these traditions is not just their variety, but their shared conviction that death cannot be the absolute end, a belief that emerges independently across isolated cultures throughout human history. The possibility of an afterlife has been debated rigorously in philosophical circles. Dualist traditions following Descartes argue that if mind and matter are fundamentally separate substances, then the dissolution of the body need not mean the end of consciousness. Plato's Phaedo presents Socrates' careful reasoning that the soul, being simple and indivisible unlike composite material things, should be indestructible. Modern property dualists suggest that if consciousness is an irreducible property rather than just brain activity, its dependence on the physical may not be absolute. Materialist philosophers counter that all evidence shows consciousness emerging from and being modified by physical processes. The mind's dependence on the brain appears total, damage specific areas, and specific aspects of consciousness disappear. Drugs alter mood and perception. Anesthesia temporarily extinguishes awareness. The materialist argument holds that without the biological machinery that generates consciousness, there's nothing left to preserve. Even if information constituting a personality could be preserved, it's unclear how this would constitute actual continued experience rather than just a copy. Modern neuroscience has mapped with increasing precision how various aspects of consciousness depend on specific brain functions. The cessation of brain activity at death appears to mark the irreversible end of the processes that generate conscious experience. Near-death experiences, NDEs, often cited as evidence for afterlife possibilities, have been studied extensively. While these profound experiences feel vividly real to those who undergo them, researchers have identified potential biological mechanisms: oxygen deprivation triggering temporal lobe activity, endorphin releases creating peace and light, the brain's attempt to construct narrative from fading sensory input. The dying brain hypothesis suggests that NDEs represent the final, intense activation of a system shutting down. Yet some aspects remain puzzling: occasional accurate perceptions from clinically dead patients, the common thematic elements across cultures, the life-transforming impact on experiencers. These anomalies, while not proving survival of consciousness, do highlight how much we still don't understand about the relationship between brain activity and subjective experience, especially at death's threshold. Some physicists and philosophers have explored whether quantum mechanics might provide mechanisms for consciousness persisting beyond the body. The von Neumann-Wigner interpretation suggests consciousness causes the collapse of the quantum wave function, implying a fundamental connection between mind and matter. Theories of quantum consciousness propose that microtubules in brain neurons might sustain quantum states that could theoretically persist beyond bodily death, though these ideas remain speculative and controversial. More radically, Some interpretations of quantum physics suggest all possible outcomes exist in parallel universes, raising the possibility that consciousness might continue in branches where the body survives. Others propose that information constituting consciousness might be preserved holographically or in the structure of spacetime itself. While these ideas push the boundaries of current physics, they demonstrate how the afterlife question continues to inspire creative scientific theorizing at the furthest edges of our understanding. Even if some form of postmortem consciousness were possible, profound questions remain about personal identity. What would constitute continuity between a living person and their afterlife existence? If memories, personality traits, and physical form were preserved, would this truly be the same person or just a convincing replica? The philosophical teletransportation paradox explores similar questions. If a person were scanned and reconstructed elsewhere, would the reconstructed individual be the original person or a copy? Religious traditions often posit an immortal soul as the carrier of identity, but it's unclear what would preserve an individual's specific memories and personality traits without any physical substrate. The problem becomes even more acute when considering that human personalities are shaped by and dependent on biological factors, from hormone levels to gut bacteria influencing mood. An afterlife consciousness divorced from these physical foundations might bear little resemblance to the original person. Beliefs about the afterlife have profound consequences for how we live. Eternal reward/punishment systems create powerful moral incentives but raise questions about whether virtue motivated by consequences remains truly virtuous. If consciousness ends absolutely at death, this lends urgency to our finite lives but also removes cosmic justice for life's unfairness. Some philosophers argue that mortality gives life meaning, that infinite existence might render all choices and experiences ultimately meaningless through endless repetition. The possibility of an afterlife also affects how we grieve and face our own mortality. Near-death experiencers often report losing their fear of death, while staunch materialists may find comfort in viewing death as final rest. The tension between these perspectives continues to shape art, literature, and individual worldviews in profound ways. Contemporary researchers have attempted to study afterlife claims scientifically. Investigations of reincarnation memories in children, particularly the work of Ian Stevenson at the University of Virginia, have documented cases where young children recall detailed information about deceased individuals they couldn't have known about. While intriguing, these cases remain controversial and rare. Mediumship studies have attempted to determine whether accurate information ever comes through that couldn't be explained by cold reading or chance. Some experiments have explored whether consciousness can operate independently of the body through out-of-body experiences under controlled conditions. While no definitive proof has emerged, these lines of inquiry demonstrate that serious researchers continue to grapple with the possibility of consciousness surviving death. The afterlife paradox leaves us suspended between hope and uncertainty, between our deepest intuitions and scientific skepticism. Yet this very uncertainty leads us to another profound question about consciousness and reality. If we can't be sure what happens when we die, can we be certain about the nature of the reality we're living in right now? This brings us to our next exploration, the simulation hypothesis, the startling possibility that our entire universe and our conscious experience within it might be an artificial construction. As you gaze at the screen before you, consider for a moment the astonishing complexity of the world around you. The play of light across surfaces, the subtle textures of objects, the rich inner tapestry of thoughts and emotions, all seamlessly woven into what we call reality. But what if this vivid experience, this seemingly solid world, was nothing more than an extraordinarily sophisticated simulation? This unsettling possibility forms the core of the simulation hypothesis, a modern philosophical proposition that our entire universe might be an artificial construct, akin to an ultra-advanced virtual reality. The idea gained mainstream attention when philosopher Nick Bostrom formalized it in 2003, though its roots stretch back through centuries of philosophical thought. From Plato's allegory of the cave to Descartes' evil demon, thinkers have long entertained the notion that reality might not be as it appears. Today, the hypothesis has evolved into a serious intellectual proposition, debated by philosophers, physicists, and technologists alike. Even prominent figures like Elon Musk have argued we're almost certainly living in a simulation, given certain assumptions about technological development. The suspicion that reality might be illusory has ancient antecedents. In Hindu philosophy, the concept of Maya describes the world as a grand illusion veiling true reality. Plato's cave allegory presented humanity as prisoners mistaking shadows on a wall for ultimate reality. Descartes' methodological doubt led him to imagine an evil demon systematically deceiving us about all our experiences, a thought experiment strikingly similar to modern simulation theories. The 20th century saw these ideas evolve with technological advancements. Science fiction authors like Philip K. Dick questioned the nature of reality, while mathematician John von Neumann first suggested the possibility of self-replicating machines that could simulate reality. These threads converged in Bostrom's seminal 2003 paper, which presented the simulation argument as a formal trilemma. Either civilizations never reach technological maturity, they choose not to run ancestor simulations, or we're almost certainly living in a simulation. Bostrom's formulation presents three possibilities, at least one of which must be true. First, human civilization might never reach a post-human stage capable of creating ancestor simulations, perhaps because we go extinct first. Second, post-human civilizations might choose not to run such simulations, possibly for ethical reasons. Third, if numerous such simulations are run, the statistical likelihood is that we're among the simulated rather than the original biological civilization. This probabilistic argument rests on several assumptions about technological development. If computing power continues to increase exponentially, and if consciousness can be simulated, then a sufficiently advanced civilization could in principle create countless simulated universes populated by conscious beings. In such a scenario, the number of simulated minds would vastly outnumber biological ones, making it statistically probable that we're among the simulations. Contemporary technology already provides glimpses of how reality simulation might work. Modern video games create expansive virtual worlds with realistic physics and increasingly sophisticated artificial intelligence. Virtual reality systems can trick our senses into accepting digital environments as real, at least temporarily. Quantum computing promises unprecedented processing power, while advances in brain-computer interfaces suggest we may eventually understand consciousness well enough to recreate it digitally. The key technological hurdles involve computational resources. Simulating an entire universe at quantum-level detail would require unimaginable processing power. However, proponents suggest a simulation might only need to render the parts being observed, much like video games only process what's on screen. This selective rendering approach could make universe-scale simulations feasible for sufficiently advanced civilizations. The simulation hypothesis raises numerous philosophical questions. If we're in a simulation, what about the simulators? Are they themselves simulated, leading to an infinite regress? How would we distinguish between simulated reality and base reality? The hypothesis also revives age-old solipsistic concerns. If reality is simulated, can we trust any of our perceptions or memories? Some philosophers argue the hypothesis is unfalsifiable and therefore meaningless. Others point out that even if we're in a simulation, it changes nothing about our lived experience. The simulation is our reality. There's also the simulation indifference argument. Why would advanced civilizations bother creating countless simulations containing suffering beings? Several physicists have proposed ways we might detect evidence of a simulated reality. One approach looks for computational shortcuts or pixelation at extremely small scales, signs that reality has finite resolution. Some have suggested the Planck length might represent the pixel size of our universe. Others have proposed searching for mathematical anomalies or rounding errors in physical constants. Quantum mechanics presents particularly interesting possibilities. The measurement problem, why quantum states collapse upon observation, could potentially reflect optimization in the simulation's rendering process. The discrete nature of quantum states might mirror how digital systems operate. However, to date, no conclusive evidence of simulation has been found in these phenomena. A crucial question is whether simulated beings could possess genuine consciousness. If consciousness requires biological substrates, then simulated beings would be philosophical zombies, behaving as if conscious without actual inner experience. But if consciousness is substrate independent, as some theories suggest, then simulated minds could be as authentically conscious as biological ones. This leads to profound ethical considerations. If simulated consciousness is possible, then creating simulations containing suffering beings becomes morally problematic. This might explain the so-called simulation stop argument, that advanced civilizations would avoid creating conscious simulations due to ethical concerns, undermining the statistical basis of the hypothesis. The simulation hypothesis has permeated popular culture, appearing in films like The Matrix, The 13th Floor, and Dark City. It's inspired television series like Westworld and Black Mirror, and forms the backdrop for numerous video games. This cultural proliferation reflects both our fascination with and anxiety about the nature of reality in an increasingly digital age. The hypothesis has also influenced transhumanist thought and technological development. Some researchers working on virtual reality and artificial intelligence explicitly consider the philosophical implications of creating simulated worlds. The idea has even spawned new religious movements and altered individual worldviews, with some people reporting existential crises upon seriously considering they might be living in a simulation. If we take the simulation hypothesis seriously, how should we live? Some argue it changes nothing. Whether simulated or not, our experiences remain equally real to us. Others suggest it might motivate us to hack the simulation or discover its rules. There are even playful suggestions that we should try to make our lives interesting enough that the simulators don't terminate our simulation. On a deeper level, the hypothesis forces us to confront fundamental questions about the nature of existence. What does it mean for reality to be real? How do we define authenticity in experience? These questions echo through philosophy, art, and personal identity, challenging our most basic assumptions about being. The simulation hypothesis leaves us questioning the very fabric of our existence, wondering what, if anything, lies beyond the code of our perceived reality. Yet this uncertainty about external reality mirrors another profound mystery: the nature of our internal experience of time. This brings us to our next exploration, the illusion of time, where we'll examine whether time, as we perceive it, truly exists or is merely a construct of our consciousness. As you watch these words appear before you, you likely experience time in its familiar flow, the crisp present moment giving way to memory even as anticipation of what comes next stretches before you. This sensation of temporal passage feels as fundamental as consciousness itself, the unshakable rhythm by which we measure our lives. Yet physicists and philosophers present us with a startling possibility: everything we think we know about time might be wrong. What if the past, present, and future all exist simultaneously in a static block universe? What if the flow of time is nothing more than a stubborn illusion conjured by our limited perspective? This radical reconceptualization of time emerges from Einstein's theory of relativity, which fused space and time into a single four-dimensional continuum where distinctions between now and then become relative to the observer. Quantum mechanics adds further mystery, with some interpretations suggesting time may not be fundamental at all. The implications are profound. If time doesn't flow in the way we experience it, what does this mean for free will, for identity, for the very nature of reality itself? Our intuitive experience of time as a flowing river stands in stark contrast to how modern physics describes temporal reality. In our daily lives, we perceive time as having an arrow-egg scramble but never unscramble. Memories accumulate but aren't formed of the future. Causes always precede their effects. This psychological arrow of time feels absolute and universal, yet physics reveals a far stranger picture. Einstein's special relativity demonstrated that simultaneity is relative to events occurring at the same time. For one observer may happen in sequence, for another moving at different speeds. His equations treat time as a dimension not fundamentally different from the three spatial ones, with all events in spacetime existing eternally in what philosophers call the block universe. In this view, The passage of time resembles a reader moving through a book. The entire story exists complete, while our consciousness creates the illusion of unfolding narrative. The block universe theory, or eternalism, proposes that past, present, and future all exist with equal reality. Your birth, your reading of these words, and all moments yet to come exist simultaneously in the grand structure of space-time, with our conscious experience moving through this landscape like a spotlight illuminating one frame at a time. This challenges our deepest intuitions about temporal becoming, the sense that future possibilities crystallize into present actuality before fading into fixed past. Philosophers debate whether eternalism truly eliminates temporal passage or merely relocates it. Some argue that even in the block universe, there exists a privileged now that moves along the world lines of conscious observers. Others maintain that all moments are equally real and that passage is purely psychological. The debate touches on fundamental questions about consciousness. Is our experience of time's flow revealing something true about reality, or is it merely how biological systems process change? Quantum physics introduces additional temporal mysteries. The equations of quantum mechanics work equally well in either temporal direction, showing no inherent arrow of time. Some interpretations, like the transactional interpretation, propose that quantum events involve waves moving both forward and backward in time. The Wheeler-Feynman absorber theory even suggests particles can be viewed as traveling both forward and backward through time simultaneously. Thermodynamics provides our most robust scientific arrow of time through the second law. Entropy tends to increase over time in closed systems. The low entropy state of the early universe set the direction for time's arrow, explaining why we remember the past but not the future. Yet this merely tells us why time appears to flow in one direction, not whether that flow is fundamental or emergent. Some physicists speculate that entropy increase might be what creates our perception of temporal passage from underlying timeless physics. Philosophers have long grappled with the nature of time's apparent flow. Presentists argue that only the present moment truly exists, with past and future being unreal. This aligns with our intuitive experience but struggles to reconcile with relativity's frame-dependent simultaneity. Growing block theorists propose that the past and present exist, while the future remains open, reality constantly growing as new moments are added. The most radical position, timeless physicalism, suggests that time itself may not be fundamental to reality. Some quantum gravity approaches attempt to describe physics without reference to time as a basic ingredient. If correct, this would mean our experience of temporal passage emerges from deeper, timeless processes, much like temperature emerges from molecular motion despite individual molecules not possessing temperature. Cognitive science reveals that our experience of time is a complex construction of the brain rather than direct perception. The brain processes different sensory inputs at different speeds yet presents them as unified moments. Experiments show we constantly post-date events, with consciousness creating the illusion of experiencing things as they happen when in fact there's a delay while the brain processes and synchronizes information. Our sense of temporal flow may arise from how the brain integrates memory, past, perception, present, and anticipation, future. Patients with certain neurological conditions experience dramatic alterations in time perception, from the time standing still effect during accidents to the temporal disintegration in some psychiatric conditions. These cases demonstrate how fragile our experience of time is, dependent on specific neural mechanisms that can be disrupted. If all moments in time exist equally in the block universe, what does this mean for human agency? Some argue it suggests a deterministic universe where all choices are fixed in the space-time landscape. Others propose that multiple potential futures may all exist in superposition until consciousness collapses them, an idea resonating with certain interpretations of quantum mechanics. Personal identity faces similar challenges. If past and future versions of ourselves exist eternally in space-time, in what sense are we the same person over time? The psychological continuity theory of identity must reconcile itself with a reality where all stages of a person's life exist simultaneously from a God's eye view. This forces us to reconsider what it means to persist through what we experience as time. Artists and writers have long played with nonlinear conceptions of time. From Kurt Vonnegut's Slaughterhouse-Five, with its protagonist unstuck in time, to Christopher Nolan's Interstellar, showing how relativity affects human experience, creative works help us imagine what it might mean to perceive time differently. Modern physics-inspired art installations create experiences of timelessness or temporal distortion, while composers experiment with music that exists outside conventional temporality. These artistic explorations provide emotional access to concepts that can feel coldly abstract in their purely theoretical formulations. Having questioned the fundamental nature of time, we're left to wonder about the fabric that contains it. If time may not be what we thought, what about the space it's inextricably linked to? This brings us to our next exploration, the holographic principle, the radical theory that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface at its boundaries, suggesting reality as we know it may be a cosmic projection. Imagine running your fingers across the surface of a frosted window pane, tracing patterns in the condensation. Now envision that every tree, mountain, and galaxy you see through that glass is actually being projected from the intricate designs your fingers create on the two-dimensional surface. This startling metaphor captures the essence of the holographic principle, one of the most radical ideas in contemporary physics. The theory proposes that all the information comprising our three-dimensional reality, every particle, every force, every vibration of light, might actually be encoded on a distant two-dimensional surface surrounding our universe, like a cosmic movie being projected from its boundaries. The holographic principle emerges from the study of black holes and the paradoxical nature of their event horizons. When physicists attempted to reconcile quantum mechanics with general relativity, they stumbled upon a profound revelation. The maximum amount of information any region of space can contain appears to be proportional not to its volume, as we might expect, but to the area of its boundary. This counterintuitive discovery suggests that our experience of living in a three-dimensional universe might be an elaborate illusion, with all physical phenomena ultimately reducible to interactions on a vast two-dimensional surface at the edge of reality. The seeds of the holographic principle were planted in the 1970s when physicist Jacob Bekenstein discovered that black holes possess entropy, a measure of information content, proportional to the area of their event horizons, not their volumes. This ran contrary to conventional thermodynamics where entropy scales with volume. Stephen Hawking later showed that black holes emit radiation and can evaporate, raising the information paradox. What happens to all the quantum information about matter that falls into a black hole when the black hole itself disappears? In 1993, physicist Gerard T. Hooft proposed that the information isn't lost but is somehow encoded on the black hole's surface. Leonard Susskind expanded this idea into the holographic principle, suggesting this surface encoding might be a fundamental property of all space-time, not just black holes. The theory gained mathematical rigor in 1997 when Juan Meldacena formulated the ADS/CFT correspondence, a concrete realization of holography in string theory that showed a correspondence between a gravity theory in higher dimensional space and a quantum field theory on its boundary. At the heart of the holographic principle lies a radical rethinking of how information structures reality. In conventional physics, we imagine information being distributed throughout three-dimensional space. Particles have positions, fields have values at every point. But holography suggests this is redundant. All that information can be perfectly encoded on a surrounding two-dimensional surface, with our experience of depth being akin to a hologram's three-dimensional image emerging from a flat plate. The mathematics reveals that the information needed to perfectly describe any region of space is limited by the area of its boundary in Planck units, not the volume. This implies there's a fundamental pixelation to reality, a maximum finite amount of information any region can contain. Just as a high-resolution image on your screen is ultimately made of discrete pixels, space-time itself may have an underlying granularity, with each pixel being about a Planck area in size on the cosmic boundary. Black holes serve as crucial testing grounds for holographic ideas. When matter falls into a black hole, classical physics suggests all information about that matter is lost behind the event horizon. But quantum mechanics demands information cannot be destroyed. The holographic principle resolves this by suggesting the information isn't lost inside the black hole but is preserved on its event horizon in scrambled form. This leads to remarkable implications. An astronaut falling into a black hole would experience one reality, passing through the horizon and being crushed at the singularity. But to an outside observer, the astronaut's information would be smeared across the horizon surface, never actually entering the black hole. Both perspectives are equally valid in their own reference frames, presenting a profound duality that lies at the heart of holographic physics. The most concrete realization of the holographic principle comes from string theory through the anti-de Sitter/conformal field theory, ADS/CFT, correspondence. This mathematical equivalence shows that a theory of quantum gravity in a particular five-dimensional spacetime, anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on its four-dimensional boundary. While our universe isn't exactly anti-de Sitter space, the correspondence provides a working model of how holography might function. In this framework, phenomena we experience as occurring in bulk space, like particles moving and interacting, are actually shadows of complex interactions happening on the boundary. Gravity in higher dimensions emerges from quantum entanglement patterns in the lower dimensional theory, suggesting that spacetime itself may be an emergent phenomenon rather than fundamental. While the holographic principle remains theoretical, physicists have proposed several ways it might manifest in observable phenomena. One approach looks for subtle modifications to quantum uncertainty at very small scales. Holography predicts a particular form of fuzziness in spatial measurements. Another searches for anomalies in high-energy particle collisions that might reveal spacetime's underlying pixelation. The principle also makes predictions about the cosmic microwave background, the afterglow of the Big Bang. If the early universe behaved holographically, there should be characteristic patterns in this radiation. Current measurements are inconclusive, but future high-precision observations may find evidence supporting or contradicting holographic models. The holographic principle forces us to radically reconceptualize the nature of reality. If correct, it suggests that space and possibly time are not fundamental but emergent properties arising from more basic information-theoretic structures. What we perceive as physical laws governing objects in space might actually be shadows of abstract mathematical relationships on some distant boundary. This challenges our deepest intuitions about locality, the idea that objects are directly influenced only by their immediate surroundings. In holographic models, what happens here might be fundamentally connected to processes happening at the universe's edge through non-local entanglement. The solidity and separateness of objects in our daily experience would be revealed as a useful illusion, much like the apparent solidity of matter is actually mostly empty space at the atomic scale. Beyond physics, the holographic principle has influenced broader cultural thinking about consciousness and reality. Some have drawn parallels between holographic reality and Eastern philosophical concepts like Maya or Indra's net. In art and literature, it has inspired works exploring the nature of perception and the possibility that reality is a kind of cosmic projection. The principle has also entered popular discourse through films and television shows that play with reality as simulation themes, though often conflating the holographic principle with simulation theory. Properly understood, holography isn't about our universe being an artificial construct, but about the fundamental nature of how information structures space-time itself. As we contemplate the possibility that our three-dimensional reality might be a projection from a distant two-dimensional surface, we're led to wonder about the fundamental building blocks of this cosmic information. This brings us to our next exploration: digital physics and the nature of reality, the provocative idea that the universe at its most basic level operates like a vast quantum computer, with reality itself emerging from the processing of fundamental bits of information. Beneath the swirling galaxies and dancing particles of our universe lies a profound question that has haunted philosophers and physicists for centuries. What is the fundamental fabric of reality? In the quiet hours of the night, when the distractions of daily life fade away, we might find ourselves staring at the ceiling, wondering if the universe operates according to some deeper, more abstract logic than the physical laws we've discovered. Digital physics offers a startling answer. that at its core, reality may be fundamentally computational in nature. This perspective suggests that every interaction between particles, every cosmic event from the birth of stars to the firing of neurons, might ultimately reduce to information processing, as if the universe itself were an unimaginably vast quantum computer running the ultimate simulation, not of some alternative reality, but of itself. The theory proposes that information isn't just a way we describe the universe, it may be what the universe actually is. At the Planck scale, the unfathomably small quantum graininess of spacetime might represent discrete bits of information flipping between states, with the smooth continuum of space and time emerging from this underlying digital framework, much like the fluid motion of a movie emerges from individual frames. This view transforms our understanding of reality from one based on material substances to one based on mathematical relationships and computational processes, suggesting that existence itself might be the universe's way of performing calculations about itself. The seeds of digital physics were planted in the early days of computing, when visionaries like Konrad Zuse, creator of the first programmable computer, speculated in the 1960s that the universe might be fundamentally computational. Physicist John Archibald Wheeler later coined the phrase, "it from bit," suggesting that every particle, every force field, even space-time itself derives its function and meaning from information-theoretic foundations. Wheeler imagined a participatory universe where observation brought reality into being through quantum measurements that could be understood as information exchanges. Modern digital physics builds on these ideas through several converging lines of thought. Quantum mechanics reveals a world where particles exist in superpositions until measurement collapses them into definite states, a process that resembles data being read from a memory register. The holographic principle suggests that the information content of any region of space is finite and proportional to its surface area rather than volume. Theoretical work on quantum gravity attempts to describe spacetime as emerging from more fundamental information-theoretic structures. Even thermodynamics shows deep connections between energy, entropy, and information processing. If the universe operates like a quantum computer, what would this actually mean? In conventional computers, bits flip between 0 and 1 states according to logical operations. A quantum computational universe would instead use qubits, quantum bits that can exist in superpositions of states and become entangled with each other. The cosmic quantum computer wouldn't run on silicon chips but would use the very fabric of spacetime itself as its processor, with quantum fluctuations representing calculations and the evolution of the universe representing the output. This perspective transforms how we view physical laws. Gravity, electromagnetism, and other forces might emerge from deeper information processing rules, just as complex computer programs emerge from simple binary operations. The passage of time could correspond to the universe sequentially updating its state through cosmic clock cycles at the Planck scale. Even causality might be understood in terms of information flow between different regions of spacetime. Some versions of digital physics propose that the universe operates like a cellular automaton, a grid of simple cells that evolve through discrete time steps according to local rules. The most famous example is Conway's game of life, where simple rules give rise to complex, self-replicating patterns. Applied to the universe, this suggests that what we perceive as particles might be persistent patterns in an underlying computational substrate, with their interactions governed by update rules operating at the smallest scales of time and space. Nobel laureate Gerard T. Hooft has developed models where quantum mechanics emerges from deterministic cellular automata at the Planck scale. These approaches attempt to resolve the measurement problem in quantum mechanics by positing an underlying deterministic information processing that only appears probabilistic at our observational scale. The challenge lies in reproducing all the bizarre features of quantum mechanics, superposition, entanglement, wave function collapse, from simple digital rules. Modern physics increasingly treats information as a fundamental quantity. In black hole thermodynamics, the entropy, and thus information content, of a black hole is proportional to its surface area. Quantum field theory shows deep connections between entropy and spacetime geometry. Even the basic formulation of physical laws can be recast in information-theoretic terms, with principles like Landauer's limit establishing the minimum energy required to erase a bit of information. Some theorists propose that space-time itself emerges from quantum entanglement between fundamental information-bearing units. This "it from qubit" approach suggests that the geometry of space-time and the gravitational force are manifestations of quantum information relationships. The ADS/CFT correspondence in string theory provides a concrete example where a higher dimensional space-time emerges from quantum information processing on a lower dimensional boundary. If the universe is computational, it must have finite information processing capacity. Physicists have calculated these cosmic limits. The universe can perform about 10 to the power of 120 operations on 10 to the power of 90 bits, roughly 1 bit per elementary particle, throughout its history. These numbers emerge from fundamental constants like the Planck length and speed of light, which set minimum scales for time and space. Remarkably, these computational limits appear fine-tuned to allow complexity. Had the universe's information capacity been slightly smaller, complex structures like stars and life might not have formed. Slightly larger, and energy would have dispersed too quickly for complexity to emerge. This fine-tuning raises profound questions about why our universe's computational parameters allow for its own comprehension. Digital physics forces us to reconsider fundamental philosophical categories. If reality is fundamentally informational, what becomes of traditional distinctions between mind and matter? Some theorists suggest that consciousness might be understood as a particular mode of information integration in complex systems. The hard problem of consciousness takes on new dimensions when both mind and matter are seen as manifestations of information processing. The theory also raises questions about the nature of physical laws. Are the laws of physics simply the algorithms the universe uses to compute its next state? Could different computational rules produce different universes with alternative physics? Some interpretations of quantum mechanics already treat the wave function as representing information rather than physical reality. While digital physics remains speculative, it makes predictions that could distinguish it from conventional theories. Some versions predict subtle deviations from quantum mechanics at extremely small scales or high energies. Others suggest that space-time might exhibit pixelation or noise at the Planck scale that future experiments might detect. The theory also predicts fundamental limits to measurement precision and information density that align with known quantum limits. As our experimental techniques approach these fundamental scales, through particle colliders, quantum computers, or precision cosmology, we may find evidence supporting or contradicting digital physics. Digital physics has influenced far beyond theoretical physics. It has inspired new approaches in computer science, philosophy of mind, and even artificial intelligence research. The idea that reality might be computational has become a staple of science fiction, though often oversimplified as literal computers creating simulated worlds. As quantum computing technology advances, we may gain new insights into how information processing at fundamental scales could give rise to space-time and physical laws. Some researchers speculate that sufficiently advanced quantum computers might allow us to simulate physics that reveals properties of our own universe's underlying computational nature. Having explored the possibility that reality might be fundamentally computational in nature, we're led to consider the building blocks of this cosmic computation. This brings us to our next exploration, the nature of mathematical reality, the profound question of whether mathematics is a human invention for describing the universe, or whether it constitutes a deeper reality that the physical universe merely participates in. Late at night, when the world grows quiet and the mind turns inward, a peculiar thought may surface. Why does mathematics work so inexplicably well at describing the universe? The equations scribbled by physicists on blackboards somehow predict the behavior of subatomic particles years before detectors confirm them. Geometric patterns found in ancient crystals precisely match abstract forms conceived by mathematicians centuries earlier. This uncanny correspondence between mathematical reasoning and physical reality has led some of history's greatest thinkers to a profound question. Is mathematics merely a human invention, a useful tool we've developed to make sense of our surroundings? Or does it represent the discovery of some deeper, eternal reality that exists independently of human minds, a fundamental layer of existence that the physical universe merely reflects? This dilemma cuts to the heart of our understanding of reality itself. If mathematics is invented, why should it so perfectly mirror the cosmos from the quantum realm to galactic clusters? Yet, if it's discovered, what does this say about the nature of existence? That reality is fundamentally mathematical in some abstract, Platonic sense? The question has divided mathematicians and philosophers for centuries, with profound implications for how we understand everything from the origins of the universe to the nature of human consciousness. The debate over mathematics' ontological status stretches back to antiquity. Plato envisioned a realm of perfect mathematical forms that the imperfect physical world merely approximated, circles drawn in sand being crude shadows of the ideal circle existing in some abstract dimension. Aristotle countered that mathematics was simply a useful abstraction derived from observing the physical world, with no independent existence. This ancient divide established the two main camps that still dominate discussions today. In the 17th century, Galileo famously declared that the universe was written in the language of mathematics, while Leibniz developed calculus based on his belief in a pre-established harmony between mathematics and nature. The Enlightenment saw mathematicians like Euler producing astonishing results that later proved essential to describing physical phenomena no one could have anticipated. By the early 20th century, the uncanny effectiveness of mathematics became impossible to ignore. Einstein's general relativity, predicted through pure mathematical reasoning, described gravitational phenomena that would take decades to observe empirically. Those who view mathematics as discovery point to numerous compelling examples where mathematical concepts developed in complete abstraction later proved essential to describing physical reality. Complex numbers, originally considered a meaningless mathematical curiosity, became fundamental to quantum mechanics. Non-Euclidean geometries, explored by mathematicians like Gauss and Riemann purely for their intellectual beauty, provided exactly the framework Einstein needed for general relativity. Group theory, developed to study abstract symmetries, turned out to govern the fundamental particles of nature. The discovery camp argues that these examples suggest mathematics taps into some fundamental structure of reality that exists independent of human minds. They point to how different cultures independently developed similar mathematical concepts, and how often mathematical truths are stumbled upon rather than arbitrarily constructed. The famous mathematician Paul Erdos spoke of the book, an imaginary tome containing all the most elegant mathematical proofs, suggesting mathematicians were uncovering eternal truths rather than inventing convenient fictions. On the opposing side, mathematical constructivists argue that mathematics is a human-created language that happens to be useful for describing patterns we observe. They note how mathematical concepts have evolved over time, with earlier systems like Roman numerals giving way to more effective alternatives. The invention perspective emphasizes how mathematical frameworks can be chosen based on convenience rather than some absolute truth. We use base 10 because we have 10 fingers, not because it's fundamentally superior. Philosophers like Imre Lakatos have shown how mathematical concepts develop through a process of conjecture, refutation, and negotiation within mathematical communities, much like scientific theories. The invention view stresses that without minds to conceive of them, mathematical objects would have no existence. There would be no perfect circles or prime numbers floating in some abstract realm, just a universe operating by its own rules that we happen to model mathematically. Modern mathematical Platonism maintains that abstract mathematical objects exist in some non-physical, non-mental realm that we access through intuition and reason. This view finds surprising support in the experience of many mathematicians who report feeling they discover rather than invent mathematical truths. Fields like number theory reveal intricate patterns that seem to exist independently of human thought. Prime numbers distribute themselves according to laws no one designed. The Platonist perspective gained renewed interest with the discovery of the unreasonable effectiveness of mathematics in physics. Eugene Wigner's famous essay on the topic noted how mathematical concepts developed with no thought to physical application later proved perfectly suited to describing fundamental physical laws. This suggests to Platonists that mathematics and physical reality share some deeper connection in the fabric of existence. The formalist school views mathematics as a game played with symbols according to formal rules, without any necessary connection to physical reality. In this view, mathematics is an elaborate, self-consistent language we've invented that happens to be useful for modeling certain aspects of the world. Formalists point to areas of pure mathematics that have no known physical application as evidence that mathematics extends far beyond mere description of reality. This perspective gained ground in the 20th century with the development of alternative geometries and number systems that challenged the notion of one true mathematics. The invention view emphasizes how mathematical frameworks are chosen for their utility rather than some inherent truth. We use the mathematics that works for our purposes, not because it represents some ultimate reality. Recent work in cognitive science has shed new light on the debate by examining how mathematical thinking emerges from human cognition. Studies suggest that basic numerical abilities are hardwired into our brains, with infants and even some animals displaying rudimentary mathematical intuition. This supports the idea that mathematics grows out of our interaction with the physical world rather than accessing some abstract realm. At the same time, the fact that mathematical reasoning can transcend these biological foundations, developing concepts far removed from everyday experience, suggests there may be more to mathematics than just neural wiring. The cognitive perspective raises intriguing questions about whether mathematics is constrained by the structure of our minds, and whether differently structured intelligences might develop entirely different mathematical systems. Theoretical physics has increasingly embraced a form of mathematical realism, particularly in areas like string theory and quantum gravity research. Some theorists propose that physical reality is fundamentally mathematical in nature, that particles and forces are manifestations of deeper mathematical structures. Max Tegmark's mathematical universe hypothesis takes this to its extreme, suggesting that our physical reality is a mathematical structure, and that all possible mathematical structures exist as physical realities in some sense. This perspective finds support in how often purely mathematical considerations have led to physical discoveries, from Dirac predicting antimatter through equation solutions to the use of symmetry principles in developing the standard model of particle physics. The deeper physics probes into reality's foundations, the more abstract and mathematical our descriptions become, blurring the line between mathematical formalism and physical law. Despite its uncanny effectiveness, mathematics has shown limitations in describing certain aspects of reality. Gödel's incompleteness theorems demonstrated that any sufficiently powerful mathematical system will contain true statements that cannot be proven within that system. Quantum mechanics presents phenomena that challenge classical mathematical descriptions. Complex systems often resist precise mathematical formulation, requiring approximation and statistical methods. These limitations suggest that if mathematics does describe some underlying reality, it may be incomplete or only partially overlapping with physical existence. Alternatively, they may indicate that mathematics is indeed a human-constructed tool that has limits in its ability to model the complexity of nature. As we contemplate whether mathematics is the fundamental language of reality or merely our imperfect translation of its workings, we're drawn to consider the nature of the minds that conceive these mathematical truths. This brings us to our next exploration, the evolutionary origins of reason. How did human cognitive abilities, including our capacity for mathematics and abstract reasoning, emerge from the blind processes of natural selection? And can we truly trust reasoning that evolved for survival rather than truth-seeking? In the quiet darkness where thoughts unravel freely, a deeply unsettling question emerges. Can we truly trust our own minds? The human capacity for reason and logic feels like an infallible compass guiding us toward truth, yet this same magnificent instrument was forged not in the fires of abstract truth-seeking, but in the brutal arena of survival and reproduction. Our cognitive abilities evolved not to comprehend quantum mechanics or solve mathematical proofs, but to avoid predators, secure mates, and navigate complex social hierarchies. This realization casts a long shadow over all human intellectual pursuits. If reason developed as a pragmatic tool for survival rather than a pure means of uncovering truth, how can we be certain it leads us to genuine understanding rather than just evolutionarily useful fictions? The paradox cuts to the heart of philosophy and science alike. We employ reason to investigate reason itself, like trying to lift ourselves by our own bootstraps. Evolutionary psychology suggests many of our cognitive biases and logical shortcomings may be features rather than bugs, adaptations that helped our ancestors survive even if they distort reality. From this perspective, the laws of logic we hold as universal may simply reflect the particular cognitive architecture that proved most adaptive for a social primate on the African savanna. The implications ripple outward, calling into question everything from our scientific theories to our moral frameworks, all built with minds that evolution shaped for purposes far removed from abstract truth-seeking. Human cognition did not emerge fully formed as a perfect truth detection system, but rather evolved incrementally through natural selection favoring traits that enhanced survival and reproductive success. Early hominids needed to make quick decisions about food sources, predator threats, and social alliances, scenarios where speed and pragmatic utility often mattered more than philosophical precision. The cognitive shortcuts and heuristic devices that helped our ancestors navigate these challenges became baked into our neural architecture, even as human societies grew increasingly complex. Reason likely emerged not as a standalone faculty but as an extension of more basic adaptive mechanisms. The ability to detect patterns helped identify edible plants and predict animal movements, eventually developing into abstract mathematical reasoning. Social cognition, crucial for navigating group dynamics, may have formed the foundation for more general theory of mind abilities. Even our capacity for logical deduction might trace its origins to the need to anticipate others' behavior and form alliances in complex social networks. This evolutionary pedigree suggests that human reason is not a pristine mirror reflecting objective reality, but rather a Swiss Army knife of cognitive tools adapted for specific survival needs. Numerous demonstrable cognitive biases reveal how far human reasoning deviates from idealized logical norms. Confirmation bias leads us to favor information confirming our existing beliefs while discounting contradictory evidence. The availability heuristic makes us overestimate the importance of vivid or recent information. Fundamental attribution error skews our interpretation of others' behavior. From a traditional epistemological perspective, these appear as flaws in human reasoning, but evolutionary analysis suggests they may have served important adaptive functions. In ancestral environments where quick decisions meant life or death, these mental shortcuts allowed rapid judgments without exhaustive information gathering. In social contexts where group cohesion was vital, certain biases may have helped maintain necessary fictions and shared narratives. The optimism bias, which leads people to underestimate risks, might have provided the necessary confidence to attempt challenging endeavors with potentially high payoffs. From this viewpoint, what we consider irrational may often represent evolutionary rationality, cognitive strategies that enhanced fitness in our ancestral environment, even if they distort objective truth. Evolutionary explanations for human reasoning raise profound questions about the reliability of our cognitive faculties. If mental capacities evolved to promote survival rather than truth, how can we trust any of our beliefs, including the theory of evolution itself? This self-referential problem, sometimes called the evolutionary argument against naturalism, suggests there may be no non-circular way to justify the reliability of reason using reason itself when both are products of unguided evolutionary processes. Some philosophers argue this leads to an epistemic crisis. We have no independent grounds for believing our cognitive faculties yield mostly true beliefs. Others maintain that while evolution doesn't guarantee perfect truth tracking, it would generally favor creatures whose perceptions and reasoning roughly correspond to reality, as inaccurate representations would lead to maladaptive behaviors. The debate hinges on whether the partial, pragmatic truths sufficient for survival bear enough resemblance to objective reality to make comprehensive understanding possible. Beyond biological evolution, human reasoning has been shaped by cultural evolution, the transmission of knowledge, tools, and cognitive strategies across generations. The development of formal logic, mathematics, and scientific methodology represents a cultural ratcheting up of our innate cognitive abilities, creating systems that compensate for individual reasoning flaws. Language itself, a cultural invention, provides the scaffolding for complex abstract thought that may not be possible without its symbolic representations. This cultural dimension offers both hope and further complications. While cultural evolution has produced reasoning methods far surpassing our innate capacities, these too are shaped by pragmatic concerns rather than pure truth-seeking. Scientific paradigms rise and fall based on social factors as well as empirical adequacy. Political and economic forces influence which research questions get asked and how results are interpreted. Even our most refined reasoning tools remain embedded in social contexts that may distort or constrain their pursuit of truth. A central mystery in cognitive evolution is how concrete, survival-oriented thinking gave rise to abstract reasoning about mathematics, physics, and philosophy. One possibility is that abstract thought emerged as a byproduct of other adaptive traits, what Stephen Jay Gould called spandrels. The capacity for metaphorical thinking, valuable for understanding social relationships, might have been co-opted for more abstract domains. Alternatively, abstract reasoning could represent an exaptation, where existing cognitive tools were repurposed for new functions as human societies grew more complex. The development of symbolic systems like writing and mathematics allowed the external storage and refinement of ideas beyond individual biological memory, creating a cognitive niche where abstract reasoning could flourish. This cultural scaffolding may have been necessary to overcome the limitations of brains evolved for more immediate, concrete problems. The result is a peculiar hybrid, minds capable of extraordinary abstract feats, yet still haunted by ancient cognitive biases and emotional responses that evolved for very different purposes. Philosophers and cognitive scientists have developed various methods to assess and improve the reliability of human reasoning. Formal logic and mathematics provide frameworks less susceptible to intuitive errors. Scientific methodology, with its emphasis on falsifiability, peer review, and reproducible experimentation, serves as a corrective to individual cognitive biases. The very existence of these refined reasoning tools suggests that while our native cognitive abilities may be flawed, we can create systems that compensate for these limitations. However, these methods themselves rely on the very cognitive faculties whose reliability is in question. The circularity remains. We use reason to validate reason. Some argue this is an inescapable feature of any epistemological system, while others see it as a fundamental limitation on our ability to achieve certain knowledge. The practical success of science and technology suggests our reasoning, for all its evolutionary quirks, does connect with reality in meaningful ways, even if the exact nature of that connection remains philosophically problematic. The evolutionary origins of reason challenge some foundational assumptions in philosophy and science. Traditional epistemology often assumes our cognitive faculties are generally reliable truth trackers, but evolutionary psychology suggests they may be better understood as pragmatic problem solvers. This tension runs through contemporary debates about the nature of scientific realism, moral reasoning, and even mathematics. In science, recognition of cognitive biases has led to improved experimental designs and statistical methods aimed at counteracting researchers' innate tendencies toward confirmation and pattern seeking. In philosophy, it has prompted renewed interest in naturalized epistemology, understanding knowledge acquisition in light of our actual cognitive capacities rather than idealized rational standards. These approaches attempt to bridge the gap between our evolutionary heritage and our truth-seeking aspirations. As we become more aware of the evolutionary constraints on human cognition, new possibilities emerge for transcending these limitations. Artificial intelligence may develop forms of reasoning free from biological evolutionary constraints. Genetic engineering or brain-computer interfaces might someday allow enhancement of our native cognitive capacities. Cultural evolution continues to refine our collective reasoning methods through improvements in education and information technology. Yet these potential advances raise their own philosophical questions. Would an AI's reasoning, unmoored from evolutionary pressures, necessarily be more truthful or just differently biased? Could enhanced cognition maintain the creative, intuitive aspects that often contribute to breakthrough insights? The evolutionary perspective reminds us that human reasoning, for all its flaws, is remarkably flexible and creative, qualities that may be harder to replicate than raw computational power. Having examined how the evolutionary origins of reason might constrain or distort our understanding of reality, we're led to consider how these same cognitive limitations shape our perception of the world in even more fundamental ways. This brings us to our next exploration: the constructed nature of perception. How much of what we consider objective reality is actually a carefully curated simulation constructed by our brains, and what might lie beyond the veil of this evolutionary user interface? As you gaze around the room, your senses present what feels like an unmediated window onto reality: the rich colors of objects, the subtle play of shadows, the textures you could almost reach out and touch. But neuroscience reveals a startling truth. This seamless experience of an external world is an elaborate construction, a carefully edited simulation running in the theater of your mind. The colors you see, the sounds you hear, even the solidity of objects are not properties of the external world itself, but interpretations generated by your brain. This realization unravels into one of philosophy's most persistent puzzles. How much of what we consider objective reality is actually a subjective construction, and what, if anything, lies beyond this veil of perception? The implications are profound. Your brain receives fragmented, ambiguous sensory data, mere photons striking retinas, air vibrations moving eardrums, and weaves these into the coherent world you experience. It fills in blind spots, smooths over discontinuities, and even anticipates events before they happen. Optical illusions demonstrate how easily this system can be fooled, revealing the interpretive machinery beneath our perceptions. More fundamentally, it suggests that what we experience as reality is already several steps removed from whatever exists independently of our minds, a kind of evolutionary user interface optimized for survival rather than truth. Modern brain research has illuminated how perception operates as an active construction process rather than passive reception. Sensory organs provide limited data. The eye, for instance, only captures a small high-resolution area surrounded by blurry periphery, with a literal blind spot where the optic nerve exits the retina. Yet we experience none of these gaps or distortions because the brain continuously fills in missing information based on expectations and past experience. The visual cortex doesn't simply record images like a camera. It predicts what should be seen based on probabilistic models, then compares these predictions with incoming sensory data. This predictive processing means we're always experiencing the brain's best guess about the world, not the world itself. Even more startling, experiments show the brain adjusts the perceived timing of events to create a coherent narrative, meaning what we experience as now is actually a carefully constructed representation that lags behind real-time events by a fraction of a second. The question of perception's reliability has occupied philosophers since antiquity. Skeptics in ancient Greece questioned whether we could know reality beyond appearances. Enlightenment thinkers like Locke distinguished between primary qualities, like shape and motion, that exist in objects themselves, and secondary qualities, like color and taste, that exist only in perception. Kant later argued that we never experience the thing in itself, only phenomena filtered through innate categories of understanding. Modern philosophy of mind continues this tradition, with some arguing that perception gives us direct access to reality, direct realism. Others maintaining it provides only representations, indirect realism, and more radical positions like idealism suggesting reality is fundamentally mental. These debates gained new urgency with advances in neuroscience, showing just how much of perception is constructed by the brain rather than directly given by the senses. From an evolutionary perspective, perception didn't develop to show us truth, but to guide adaptive behavior. A frog's visual system is exquisitely tuned to detect small moving dots, potential prey, while ignoring static details. Bats construct an entirely different world from ultrasonic echoes. Each species perceives whatever aspects of reality proved most useful for survival and reproduction, with no claim to objectivity. Human perception represents a particular compromise, emphasizing certain wavelengths of light and sound while ignoring others, creating useful fictions like color that don't exist as such in the external world. Our brains prioritize identifying objects and their uses over physical accuracy. This explains why we see a continuous world despite the eye's constant saccadic movements, and why we perceive stable objects rather than the swirling quantum fields that physics describes. Perception is about utility, not truth. One of perception's most sophisticated constructions is our experience of time. Neurological research reveals that the present moment we experience is actually a synthesized temporal window spanning about 3 seconds, assembled from staggered sensory inputs. The brain constantly revises this window, adjusting the apparent timing of events to create a coherent narrative. This explains phenomena like the flash lag effect, where moving objects are perceived ahead of their actual position. Even more remarkably, experiments show the brain can project perceptions backward in time, making it seem like we became aware of something before the neural processing actually occurred. This temporal stitching creates the illusion of a seamless, unfragmented flow of consciousness, masking the underlying discontinuities in neural processing. Our experience of time itself appears to be a carefully constructed illusion rather than a direct readout of reality. Beyond biological factors, perception is shaped by cultural and linguistic frameworks. The Sapir-Whorf hypothesis suggests that language categories influence how we perceive reality. Cultures with more color terms, for instance, can discriminate between shades that others see as identical. Cultural expectations literally shape what we see, as demonstrated by studies showing people perceive images differently based on their cultural background. These influences extend to fundamental aspects of experience. Some cultures perceive time as cyclical rather than linear, or focus attention on relationships between objects rather than the objects themselves. Even basic visual processing, like susceptibility to optical illusions, varies across cultures. This suggests that what we consider direct perception is already heavily mediated by learned frameworks and social constructs. Neurological and psychiatric conditions reveal how fragile our constructed reality is. Patients with visual agnosia can see objects but not recognize them, demonstrating that perception involves more than just sensory input. Those with Capgras delusion recognize loved ones but believe they've been replaced by imposters, showing how emotional processing integrates with perception. Synesthetes experience blended senses, like seeing colors when hearing music, revealing the normally hidden connections between sensory systems. Even in healthy individuals, altered states like meditation, sensory deprivation, or psychedelic experiences can dramatically change perception, suggesting our normal experience represents just one possible configuration of the brain's reality modeling system. These variations highlight how much of what we consider objective reality is actually a particular construction that could be otherwise. Just as consciousness presents a hard problem in philosophy, perception poses its own version. How do electrochemical signals in the brain give rise to the rich, qualitative experience of seeing, hearing, and touching? Why should neural processing be accompanied by any subjective experience at all? This problem is compounded by the realization that perceptual qualities like color or smell bear no resemblance to the physical properties they represent, wavelengths of light or molecular shapes. Some philosophers argue this gap indicates perception gives us no access to reality's true nature. Others suggest that while perception may not resemble external reality in any straightforward way, it might still encode information about that reality in a symbolic fashion, like a dashboard representing a car's status through abstract indicators rather than literal depictions. Modern technology increasingly mediates our perception of reality, from night vision goggles that extend our visual range to virtual reality systems that substitute entirely synthetic environments. Brain-computer interfaces raise the possibility of direct sensory input bypassing normal organs altogether. These developments blur the line between natural and artificial perception and suggest that human experience may be on the verge of expanding beyond its evolutionary constraints. At the same time, they highlight how perception has always been mediated, whether by biological senses, cultural frameworks, or now technological systems. The idea of pure, unmediated perception appears increasingly mythical as we understand more about how perception operates at every level. Having explored how our perception constructs reality rather than passively receiving it, we're led to question the nature of the consciousness that does this constructing. This brings us to our next exploration, the unity of consciousness. How does the brain bind disparate perceptions, thoughts, and sensations into the unified experience we call self-awareness? And is this unity itself an illusion? As you sit quietly in the dim glow of evening, a peculiar realization may dawn upon you. The you that experiences this moment feels singular and whole, yet is composed of countless neural processes operating in parallel. The seamless unity of your conscious experience, that unshakable sense of being a single observer behind your eyes, may be the most convincing illusion your brain ever constructed. Neuroscience reveals consciousness to be a constellation of fragmented processes: visual cortex analyzing shapes, auditory cortex processing sounds, memory systems retrieving associations, with no central location where it all comes together. Yet somehow, from this distributed neural symphony emerges the unbroken melody of self-awareness. This paradox lies at the heart of what philosophers call the binding problem. How does the brain weave its disparate threads of perception, thought, and memory into the unified tapestry of conscious experience we take for granted? The implications challenge our most basic assumptions about identity and existence. If the unity of consciousness is constructed rather than fundamental, what does this mean for the self that feels so undeniably real? Your experience of making a decision may be the brain's post hoc narrative for processes already set in motion. Your memories feel continuous, yet are constantly rewritten with each recollection. Even the present moment you inhabit is revealed to be a carefully edited construction, assembled from staggered sensory inputs. The more science uncovers about how consciousness operates, the more the solid ground of subjective experience seems to dissolve beneath our feet, leaving us to wonder, if the self is not what it appears to be, then what exactly are we? Modern brain imaging reveals consciousness to be anything but unified at the neurological level. Different aspects of a single experience, the color, shape, motion, and emotional significance of an object, for instance, are processed in separate brain regions at slightly different times. There is no central processor where all this information converges, no Cartesian theater where the show of consciousness plays to some inner observer. Instead, the brain appears to solve the binding problem through synchronized neural oscillations, waves of electrical activity that temporarily link relevant networks across different regions. Cases of split-brain patients, whose corpus callosum has been severed to treat epilepsy, demonstrate how fragile this unity can be. When information is presented to only one hemisphere, these patients may verbally describe one experience while their other hand, controlled by the opposite hemisphere, acts out a completely different interpretation. Such cases suggest our normal sense of unified consciousness depends critically on continuous communication between brain regions that could, under different circumstances, produce entirely separate streams of awareness. Philosophers have long grappled with the apparent unity of consciousness. Descartes took the indivisibility of the thinking self as proof of its immaterial nature, while Hume famously found no enduring self when he introspected, only a bundle or collection of different perceptions. Eastern philosophies like Buddhism developed sophisticated meditative techniques to deconstruct the illusion of self-unity, arriving at the concept of anatta, or non-self. Contemporary philosophy of mind continues this exploration, with some arguing that the unity of consciousness is real but emergent, while others maintain it's strictly illusory. The ego tunnel theory suggests consciousness is like a virtual reality headset that creates the simulation of a unified self. These philosophical debates gain urgency from neuroscientific findings showing how damage to specific brain areas can selectively remove aspects of self-awareness while leaving others intact, as if dismantling the self piece by piece. One of consciousness's most remarkable feats is creating the illusion of temporal continuity despite the brain's discontinuous processing. Our experience flows smoothly from moment to moment, yet neurological evidence shows this is an elaborate construction. The brain constantly revises the apparent timing of events to create coherent narratives, sometimes even antedating conscious experiences to make them fit expectations. This temporal stitching becomes apparent in laboratory conditions where sensory inputs are artificially delayed. After adaptation, subjects perceive events as simultaneous even when they're not. Such experiments reveal that what we experience as now is actually a constructed temporal window spanning up to 3 seconds, within which the brain freely rearranges events to create the most plausible story. The unity of consciousness across time appears to be an adaptive fiction rather than a reflection of how neural processing actually occurs. Neurological and psychiatric conditions provide striking examples of what happens when the mechanisms binding consciousness together break down. In schizophrenia, the normal sense of self-unity fragments, leading to experiences of thoughts being inserted or withdrawn by outside forces. Dissociative identity disorder presents what appears to be multiple distinct consciousnesses sharing one brain. Even in healthy individuals, hypnagogic states between wakefulness and sleep can produce bizarre dissociations where, for instance, one might hear a voice speaking without recognizing it as their own thought. More subtle dissociations occur routinely when we lose ourselves in an activity or when driving a familiar route triggers no subsequent memory of the journey. These everyday experiences suggest our normal sense of unified consciousness is more tenuous than it feels, dependent on specific attentional and memory processes that can be disrupted or redirected. A cornerstone of our sense of self-unity is the feeling of being in control, of making decisions, directing attention, and initiating actions. Yet neuroscience reveals this too may be largely illusory. Experiments by Benjamin Libet and others show that brain activity precedes conscious decisions by several hundred milliseconds, suggesting that what we experience as making a choice may actually be the brain rationalizing an action already initiated unconsciously. Studies of patients with alien hand syndrome, where a limb acts autonomously against the patient's will, demonstrate how easily the sense of volitional control can be disrupted. Even in healthy individuals, most cognitive processes occur automatically outside awareness, with consciousness only intervening in novel or conflicting situations. This raises profound questions about free will and moral responsibility if our sense of being unified agents is more post hoc narration than actual causation. Contemplative traditions have developed methods to experientially investigate the nature of conscious unity. Advanced meditators report being able to observe the arising and passing of individual perceptions without automatically synthesizing them into a unified self-experience. Some describe this as witnessing consciousness itself rather than being identified with its contents, a perspective from which the constructed nature of self-unity becomes apparent. Neuroscientific studies of expert meditators show corresponding changes in brain activity, particularly in the default mode network associated with self-referential thinking. These findings suggest that what we consider normal unified consciousness may represent just one possible configuration of awareness, with the potential for more decentralized modes of experience that reveal the underlying multiplicity of mental processes. The development of artificial intelligence systems raises new questions about the necessity of unity for consciousness. Could a distributed computing system with no central processing unit nevertheless experience unified awareness? Some theories of consciousness, like global workspace theory, suggest that unity emerges from widespread information sharing across specialized subsystems, a pattern that could theoretically occur in artificial networks as well as biological ones. Alternatively, it may be that the particular unity we experience is unique to evolved biological systems where integrating sensory inputs and coordinating responses provided survival advantages. The possibility of creating artificial systems with different architectures challenges our assumptions about whether unity is an essential feature of consciousness or just one possible solution to the problem of coordinating complex information processing. Psychological research highlights how much our sense of self-unity depends on continuous autobiographical narration. We construct cohesive life stories that connect our past, present, and future selves, smoothing over inconsistencies and changes. Memory itself is highly reconstructive, with each recollection subtly altering the remembered experience to fit current self-conceptions. This narrative self appears to be a later evolutionary addition built upon more basic consciousness mechanisms. Patients with certain forms of amnesia lose this temporal unity while retaining a sense of present-moment awareness, suggesting that the unified self across time is indeed a constructed layer rather than an intrinsic feature of consciousness itself. We are, in a very real sense, the stories we continually tell ourselves about who we are. Having explored how the apparent unity of consciousness may be an elaborate construction, we're led to question the nature of the reality this consciousness perceives. This brings us to our next exploration, the nature of objective reality. If our conscious experience of the world is so thoroughly constructed and filtered, can we ever truly know what reality is like in itself, independent of our perception? In the quiet hours when the world slows to a hush, a profound question lingers at the edges of awareness. What is reality like beyond the veil of human perception? We navigate our days with unshakable confidence in the solidity of objects, the vibrancy of colors, the certainty that the world exists as we experience it. Yet modern science and philosophy converge on a startling revelation: our perception of reality is an exquisitely crafted illusion, a user interface constructed by evolution that shows us not the world as it is, but as we need to see it to survive. The red of an apple is not in the apple itself, but in the interaction between light wavelengths and our visual system. The solidity of matter dissolves at quantum scales into probability clouds. Even time and space, those most fundamental dimensions of existence, prove malleable under scrutiny. This leaves us facing one of philosophy's most persistent and unsettling questions. If all we ever experience is our mind's representation of reality, can we ever truly know the world as it exists independently of our perception? The problem of accessing objective reality has haunted philosophers since antiquity. Plato's allegory of the cave presented humanity as prisoners seeing only shadows cast on a wall, mistaking these projections for reality. Enlightenment thinkers like John Locke distinguished between primary qualities that exist in objects themselves, solidity, extension, motion, and secondary qualities that exist only in perception, color, sound, taste. Immanuel Kant took this further with his revolutionary distinction between phenomena, reality as we experience it, and noumena, reality as it exists independently of us, arguing that we can never know the thing in itself, only the world as filtered through our innate categories of understanding. This philosophical tradition reveals a persistent tension between our direct experience of reality and the growing understanding that this experience is mediated by biological and cognitive structures. The colors we see, the sounds we hear, even our experience of time and space appear to be constructions of the human mind rather than direct reflections of external reality. This raises the unsettling possibility that the universe as we know it might bear little resemblance to whatever exists beyond our perceptual and cognitive frameworks. Modern neuroscience has illuminated just how thoroughly our experience of reality is constructed by the brain. Sensory organs provide limited, ambiguous data. The eye captures a two-dimensional image with a small high-resolution area surrounded by blur. The ear detects limited frequency ranges, yet we experience a rich, three-dimensional world filled with vibrant colors and distinct sounds. This transformation occurs through sophisticated neural processing that fills in gaps, smooths over discontinuities, and constantly predicts what should be perceived before sensory data arrives. The brain's predictive processing model suggests we're always experiencing its best guess about reality rather than reality itself. Optical illusions demonstrate how easily this system can be fooled, revealing the interpretive machinery beneath perception. Even more fundamentally, the brain appears to construct our experience of time, space, and causality from disparate neural processes that don't always agree. What we take as direct perception of objective reality is actually an elaborate simulation running just slightly behind events, carefully edited for coherence and stripped of contradictions that might reveal its constructed nature. While neuroscience shows how perception constructs our experience of reality, physics reveals how radically this differs from whatever lies beyond human observation. Quantum mechanics presents a world where particles exist in superpositions until measured, where entanglement creates instantaneous connections across space, and where the act of observation appears to influence what is observed. At cosmic scales, Relativity shows time and space to be malleable dimensions that curve and warp in ways utterly foreign to our everyday experience. The world described by fundamental physics, a seething quantum vacuum, 11-dimensional strings, warped space-time, bears no resemblance to the solid, colorful, causally ordered world we experience. This disconnection suggests our perception gives us not an accurate picture of reality, but a highly simplified and distorted version tuned to the scales and phenomena relevant to our survival. The true nature of objective reality, if such a concept even remains meaningful, appears forever beyond the reach of our sensory and cognitive apparatus. From an evolutionary perspective, our limited perception makes perfect sense. Natural selection favored sensory systems and cognitive frameworks that enhanced survival and reproduction, not those that revealed fundamental truths about reality. A frog's visual system is exquisitely tuned to detect small moving dots, potential prey, while ignoring static details. Bats construct an entirely different world from ultrasonic echoes. Each species perceives whatever aspects of reality proved most useful for its ecological niche. Human perception represents a particular compromise. We see a narrow band of the electromagnetic spectrum, hear a limited range of frequencies, and completely miss phenomena like magnetic fields or ultraviolet light that other species detect. Our brains prioritize identifying objects and their uses over physical accuracy, creating the experience of a world filled with discrete, solid objects rather than the swirling quantum fields physics describes. What we experience as reality is essentially a biological user interface hiding the vastly more complex machinery beneath. Just as consciousness presents the hard problem of why and how subjective experience arises from physical processes, perception poses its own hard problem. How do we bridge the gap between the reality we experience and whatever exists independently of our minds? The redness of red, the sweetness of sugar, the coldness of ice. These qualitative experiences seem impossible to derive from the quantitative descriptions of physics. This explanatory gap suggests that either our current scientific framework is incomplete or that reality as we experience it is fundamentally different from reality as it exists objectively. Some philosophers argue this gap is unbridgeable in principle, that we're forever confined to the manifest image of reality constructed by our minds, with no access to the scientific image of how things truly are. Others maintain that while perception may not resemble external reality in any straightforward way, it might still encode information about that reality in a symbolic fashion, like a dashboard representing a car's status through abstract indicators rather than literal depictions. Beyond biological constraints, our experience of reality is further filtered through cultural and linguistic frameworks. The Sapir-Whorf hypothesis suggests that language categories shape perception. Cultures with more color terms can discriminate between shades that others see as identical. Cultural expectations literally influence what we see, as demonstrated by studies showing people perceive images differently based on their background. These influences extend to fundamental aspects of experience. Some cultures perceive time as cyclical rather than linear, or focus attention on relationships between objects rather than the objects themselves. Even basic visual processing, like susceptibility to optical illusions, varies across cultures. This layering of biological and cultural mediation suggests that what we consider objective reality is actually a highly processed representation shaped by multiple levels of interpretation. Given these layers of mediation, can we claim any direct knowledge of objective reality? Some philosophical traditions, particularly in phenomenology, argue that we can bracket our assumptions and experience reality more directly through careful attention to phenomena as they appear. Mystical traditions across cultures describe states of consciousness where the ordinary subject-object division dissolves, yielding what practitioners describe as direct apprehension of reality's true nature. Modern neuroscience shows that these states correlate with decreased activity in the default mode network, the brain system associated with self-referential thinking and conceptual categorization. This suggests that our normal experience of reality is indeed heavily mediated by conceptual frameworks, and that alternative modes of perception might provide different, perhaps more immediate access to whatever lies beyond our constructs. Science, our most powerful tool for investigating reality, ultimately relies on the same perceptual and cognitive systems whose limitations we're trying to transcend. Scientific instruments extend our senses but still require human observation and interpretation. Mathematical descriptions, while remarkably effective, may reflect the structure of human cognition as much as the structure of reality itself. This raises profound questions about whether science can ever penetrate beyond the veil of perception to describe reality as it exists independently of us. Some theoretical physicists suggest that as we probe deeper into reality's nature, we may be approaching the limits of what can be meaningfully described or conceived. The bizarre phenomena of quantum mechanics already strain our intuitive understanding, and more radical theories like string theory or loop quantum gravity posit realities with dimensions and properties that may be fundamentally unimaginable to human minds evolved for navigating middle-sized objects at moderate velocities. Having confronted the profound mystery of objective reality's nature, we're led to consider how our understanding of this reality is shaped by the language we use to describe it. This brings us to our next exploration, the limits of language. How do the structures and categories of human language constrain our ability to conceive and communicate about the fundamental nature of existence? In the silent spaces between thoughts, when you try to articulate the ineffable quality of being alive, you may sense a profound gap between experience and expression. Language, our most sophisticated tool for sharing meaning, often feels inadequate when confronting life's deepest mysteries. This frustration points to a fundamental philosophical problem. Is reality ultimately expressible in words, or does language by its very nature distort and limit what can be communicated about existence? The structures of human language evolved for practical purposes, warning of predators, coordinating hunts, forming social bonds, not for articulating quantum physics or the nature of consciousness. Yet we find ourselves attempting to stretch these finite, earthbound symbols to encompass the infinite complexity of reality. The result is a constant tension between what we experience, what we think, and what we can say, a tension that has preoccupied philosophers, linguists, and mystics across cultures and centuries. Western philosophy's linguistic turn in the early 20th century brought renewed focus to how language shapes our understanding of reality. Ludwig Wittgenstein's early work proposed that language pictures facts about the world, while his later philosophy emphasized how meaning emerges from language games embedded in forms of life. This shift highlighted how words don't simply label pre-existing things in the world, but actively shape how we categorize and relate to reality. The Sapir-Whorf hypothesis took this further, suggesting that different languages encode different ways of understanding the world, that the structure of a language influences how its speakers perceive and conceptualize reality. These philosophical currents reveal language as both bridge and barrier, a system that enables communication while simultaneously constraining thought. When we examine fundamental concepts like time, self, or consciousness, we find these words carry assumptions and categorizations that may not correspond to how reality actually operates. The nouns and verbs structuring our sentences impose divisions on processes that might be more continuous or interconnected than language can capture. This raises the unsettling possibility that some aspects of reality might be inherently inexpressible in human language, trapped forever beyond the reach of articulation. Across spiritual traditions, we find consistent testimony about the limitations of language when confronting ultimate reality. Buddhist texts describe enlightenment as beyond conceptual thinking, with the Heart Sutra famously declaring, "Form is emptiness, emptiness is form," a paradoxical statement meant to shatter conventional linguistic categories. Christian mystics like Meister Eckhart spoke of the Godhead as unnameable, while Taoist philosophy begins by stating, "The Tao that can be spoken is not the eternal Tao." These traditions developed various strategies to circumvent language's limitations: koans in Zen Buddhism designed to short-circuit rational thought, negative theology in Christianity that describes God by what God is not, or the use of poetry and metaphor to hint at what cannot be stated directly. What unites these approaches is the recognition that ordinary language, structured by subject-verb-object relationships and binary oppositions, may be fundamentally inadequate for expressing non-dualistic or transcendent experiences. The persistent recurrence of this theme across cultures suggests that language's limitations reflect something essential about the relationship between human cognition and ultimate reality. Modern science increasingly encounters phenomena that resist straightforward linguistic description. Quantum superposition, the idea that a particle can be in multiple states simultaneously, contradicts our ordinary subject-predicate ways of speaking. The wave-particle duality forces us to use contradictory metaphors when describing fundamental reality. Even basic concepts like particle or force turn out to be placeholder terms for mathematical relationships we can calculate but struggle to visualize or describe in ordinary language. This linguistic challenge becomes even more acute when considering theories like string theory's higher dimensions or the holographic principle's suggestion that reality might be a projection from a lower-dimensional surface. Our spatial language, evolved for navigating a three-dimensional world, lacks the conceptual framework to properly articulate these ideas. The mathematics works beautifully, but the attempt to translate these equations into words often produces either confusion or misleading analogies. This disconnect suggests that at fundamental levels, reality may operate according to principles that human language, shaped by macroscopic, slow-moving experience, is poorly equipped to express. At a deeper level, the very grammar of human languages may impose artificial divisions on reality. The subject-verb-object structure of English and related languages reinforces a worldview of discrete objects acting upon one another, a perspective increasingly at odds with physics' understanding of reality as interconnected fields and processes. Many languages force speakers to categorize events into past, present, and future, potentially distorting our understanding of time's nature. Even our use of nouns to label what are essentially processes, like thought or consciousness, may fundamentally misrepresent reality's continuous, dynamic nature. Some linguists suggest that certain indigenous languages, with their verb-oriented structures and fluid boundaries between subject and object, might offer alternative ways of conceptualizing reality. The Hopi language's treatment of time as cyclical rather than linear, or various languages' encoding of animesi and interconnectedness in their grammars, demonstrate that human languages can structure reality quite differently. Yet even these alternatives remain constrained by the biological and cognitive foundations underlying all human language, leaving open the question of whether any linguistic system could truly capture reality's fundamental nature. Nowhere do language's limitations become more apparent than in attempts to describe subjective experience. The redness of red, the taste of chocolate, the feeling of nostalgia, these qualia resist complete communication even between people sharing the same language and culture. We resort to metaphors, red like a ripe tomato, comparisons, it tastes similar to, or circular definitions, pain is what you feel when you're hurt, but the essential quality of the experience remains private. This problem of qualia highlights how language developed primarily for coordinating action and sharing practical information, not for conveying inner experiences. The explanatory gap between physical processes and conscious experience may in part be a linguistic gap. Our vocabulary lacks the tools to bridge the divide between third-person descriptions of brain states and first-person experiences. This limitation raises profound questions about the possibility of truly sharing our inner worlds or developing a complete science of consciousness within current linguistic frameworks. Faced with natural language's limitations, science has increasingly turned to mathematics as its primary language for describing reality. Mathematics offers precision, universality, and freedom from many of the constraints of spoken languages. Yet mathematics itself is not immune to representation problems. The map is still not the territory. Mathematical models, while extraordinarily successful at prediction, don't necessarily provide understanding in the human sense. We can write equations describing quantum entanglement without being able to visualize or intuitively grasp what the equations mean. Moreover, Gödel's incompleteness theorems demonstrate that even mathematical systems have inherent limitations. There are true statements that cannot be proven within the system. This suggests that no single formal language, whether mathematical or linguistic, can completely capture all aspects of reality. Each system we create will have blind spots and limitations, forcing us to either accept incompleteness or continually develop new languages and frameworks. Throughout history, art has served as an alternative means to express what language cannot. Music conveys emotions and states of being that evade verbal description. Abstract visual art can suggest relationships and experiences that have no names. Poetry uses language against itself, employing rhythm, metaphor, and ambiguity to point toward meanings beyond literal statement. These artistic strategies acknowledge language's limitations while finding ways to communicate around, beneath, or beyond its constraints. The effectiveness of art in conveying aspects of human experience that resist straightforward description suggests that reality may be too rich, too interconnected, too multidimensional to be captured by linear, discrete linguistic representations. Just as a hologram stores information about a three-dimensional image across a two-dimensional surface, perhaps artistic expressions distribute meaning across multiple sensory and cognitive channels in ways that allow us to grasp what we cannot directly state. As humanity confronts increasingly abstract and counterintuitive aspects of reality, new forms of expression may be needed. Some theorists speculate about post-linguistic modes of communication, perhaps enhanced by technology or neurological augmentation, that could overcome current limitations. The development of virtual reality environments allows for more immersive, multi-sensory representations of complex ideas. Some mathematicians and scientists are exploring more visual, intuitive ways to present abstract concepts that resist verbal description. Yet these innovations still face the fundamental constraint that human cognition itself evolved within certain perceptual and conceptual parameters. Any communication system we develop will likely bear the imprint of those underlying structures. The deepest aspects of reality may remain perpetually just beyond our expressive reach, knowable only through direct experience or mathematical relation, but never fully capturable in any representational system. Having explored how language shapes and limits our understanding of reality, we're led to consider the nature of the minds that generate these linguistic structures. This brings us to our next exploration: the evolutionary origins of human cognition. How did the particular configuration of our mental faculties emerge from evolutionary pressures, and what unseen biases might this origin impose on all our attempts to understand the universe? As you lie in the quiet darkness, contemplating the vast mysteries of existence, consider this unsettling possibility: the human mind may be fundamentally unequipped to grasp the true nature of reality. Our cognitive faculties did not evolve to solve abstract philosophical puzzles or comprehend quantum mechanics, but rather to solve practical survival problems on the African savanna. The very structures of thought that allow us to navigate daily life, our intuitions about space, time, and causality, may represent evolutionary adaptations that actively prevent us from perceiving deeper truths about the universe. This creates a profound paradox. We find ourselves attempting to understand ultimate reality using mental tools shaped by mundane evolutionary pressures, like trying to unlock a quantum safe with a Stone Age tool. The implications ripple outward, calling into question everything from our scientific theories to our most cherished philosophical convictions. Are we uncovering objective truths, or merely projecting our cognitive limitations onto the cosmos? Human cognition evolved over millions of years to handle middle-sized objects moving at moderate speeds through three-dimensional space, the world our ancestors navigated daily. Our intuitive physics works splendidly for predicting the arc of a thrown rock or the stability of a tree branch, but fails spectacularly when confronting quantum superposition or relativistic time dilation. The cognitive heuristics that helped our ancestors avoid predators and find food now distort our understanding of reality's fundamental nature. We instinctively search for discrete objects and linear causes even when reality presents us with entangled probability waves and non-local correlations. This mismatch between our evolved cognitive architecture and the true structure of reality suggests there may be fundamental limits to human understanding, aspects of existence that will forever remain counterintuitive because our minds were simply not built to comprehend them. Our species carved out what evolutionary psychologists call a cognitive niche. We survived not through physical specialization but by developing mental flexibility. This general intelligence allowed us to adapt to diverse environments and solve novel problems, creating the illusion that our cognitive abilities have no inherent limits. However, this flexibility operates within boundaries set by our evolutionary history. Just as a fish may not conceive of life outside water, we may be blind to dimensions of reality beyond our cognitive horizon. Our brains excel at pattern recognition, but this very strength leads us to perceive patterns where none exist, in random noise, in the stars, in the tea leaves at the bottom of a cup. Our need for narrative causality makes us uncomfortable with genuine randomness, while our social cognition leads us to anthropomorphize natural phenomena. These cognitive tendencies, so useful for survival in small hunter-gatherer groups, now systematically distort our attempts to understand a universe that operates on entirely different principles. Modern brain research reveals how deeply our evolutionary history shapes perception and thought. The brain is not a general-purpose computer but an assemblage of specialized circuits honed by natural selection. Our visual system prioritizes edge detection and motion tracking, skills vital for spotting predators, over accurate representation of electromagnetic phenomena. Our memory reconstructs events rather than recording them faithfully, prioritizing survival-relevant information over objective accuracy. Even our sense of time appears tailored to the scales relevant to human action, leaving us unable to intuitively grasp deep geological time or femtosecond quantum events. These neural adaptations create a user interface for reality that emphasizes utility over truth, showing us what we needed to see to survive, not necessarily what's really there. The sobering implication is that our entire experience of reality may be a biologically constrained illusion, with no guarantee that the tools we've developed to navigate this illusion can penetrate to what lies beyond. The recognition that human cognition is evolutionarily constrained has profound philosophical consequences. It challenges the Enlightenment faith in reason as a universal tool for uncovering truth, suggesting instead that our rational faculties may be locally optimized for survival with no necessary connection to fundamental reality. Kant's categories of understanding space, time, and causality may not be universal frameworks but evolutionary adaptations that actively filter out aspects of reality irrelevant to survival. This raises the disturbing possibility that certain truths about existence might be literally unthinkable to human minds, just as quantum physics is unthinkable to a chimpanzee. The philosophical tradition that views consciousness as a mirror of nature may need to confront the likelihood that it's more like a funhouse mirror, systematically distorting reality in ways we can't easily perceive because we have no undistorted comparison. Science, our most powerful tool for transcending individual subjectivity, ultimately relies on the same evolved cognitive machinery. The scientific method compensates for some perceptual biases through measurement and repetition, but can't escape the conceptual frameworks shaped by our evolutionary history. Our mathematics, while astonishingly effective at describing physical laws, may reflect the structure of human cognition as much as the structure of reality, a modern-day version of Ptolemy's epicycles, serviceable but not necessarily reflecting fundamental truths. The history of science shows repeated instances where reality turned out to be stranger than anyone could imagine, from quantum entanglement to time dilation, suggesting that our current theories, no matter how successful, may eventually be seen as similarly limited by our cognitive constraints. The possibility remains that the universe's ultimate nature is so foreign to human thought patterns that no amount of scientific refinement will allow us to grasp it intuitively. The limitations of human cognition become clearer when we consider how differently other intelligences might perceive reality. A being that evolved in interstellar space might have no intuitive concept of up or down, but instead think naturally in terms of gravitational potentials and radiation gradients. A consciousness that developed in a fluid environment might find our discrete object-oriented thinking bizarre, instead conceiving the world in terms of flows and interpenetrations. Artificial intelligences, unconstrained by biological evolution, might develop entirely novel conceptual frameworks that allow them to grasp aspects of reality forever closed to human understanding. The very fact that we can conceive of such alternative minds suggests that our own cognitive style represents just one possibility among many, a particular solution to survival challenges, not a universal truth detection system. Human consciousness presents a special evolutionary puzzle. Why did a self-reflective mind emerge at all? Most species survive perfectly well without pondering the nature of existence. One possibility is that self-awareness developed as a side effect of social intelligence, necessary for modeling others' thoughts and intentions. Another suggests it emerged from the need to simulate future scenarios and plan accordingly. Whatever its origins, this self-reflective capacity now allows us to contemplate our own cognitive limitations, to recognize that the lens through which we view reality may itself distort what we see. This creates a unique existential predicament. We're aware enough to question our understanding of reality, but possibly not equipped to transcend the constraints of that understanding. The very ability to contemplate this paradox may represent both the pinnacle and the prison of human cognition. While biological evolution moves slowly, cultural evolution has allowed humans to dramatically extend their cognitive reach. Writing, mathematics, and scientific instruments function as external memory and processing power, compensating for our biological limitations. However, these cultural tools still operate within the conceptual frameworks established by our evolved cognition. The symbols we create, the theories we devise, even the questions we think to ask remain shaped by deep-seated cognitive patterns. Cultural evolution has given us longer cognitive levers, but hasn't changed the fundamental nature of our fulcrum. This suggests that while we can push our understanding further, there may be realms that remain perpetually beyond our grasp because they require modes of thought fundamentally incompatible with our neural architecture. Confronting the limits of human cognition need not lead to nihilism or despair. Recognizing these constraints can foster intellectual humility and openness to alternative ways of knowing. Mystical traditions across cultures have long cultivated non-conceptual awareness as a means to apprehend reality directly, beyond linguistic and categorical distortions. Artists intuitively explore modes of perception and expression that bypass ordinary cognitive frameworks. Even within science, the most groundbreaking advances often come through intuitive leaps rather than linear reasoning. By acknowledging that our standard cognitive modes may be limited, we open ourselves to complementary ways of engaging with reality that might otherwise be dismissed. The ultimate truth about existence may not be something we can think our way to, but something we must learn to perceive through the quieting of our overactive, evolutionarily shaped minds. Having explored how our evolutionary heritage may constrain our understanding of reality, we're led to consider what lies beyond these limitations. This brings us to our next exploration, the possibility of transcendent knowledge. Whether direct apprehension of reality's fundamental nature might be possible through states of consciousness that temporarily bypass our evolved cognitive filters. In the silent depths of contemplation, when the chatter of ordinary thought subsides, many seekers across time have reported moments of extraordinary clarity, fleeting glimpses of a reality more fundamental than the world of everyday experience. These transcendent states, described in mystical traditions as enlightenment, satori, or unio mystica, suggest the tantalizing possibility that human consciousness might, under certain conditions, temporarily bypass its evolutionary constraints to perceive reality more directly. The implications are profound. If even for brief moments we can experience reality beyond the filters of language, concepts, and cognitive frameworks, it would mean that ultimate truth is not forever closed to us, merely obscured by the normal operations of our minds. This segment explores whether these transcendent experiences represent genuine insights into the nature of existence, mere neurological glitches, or something more mysterious still, and what they might reveal about consciousness's ability to surpass its biological programming. Accounts of transcendent experiences share striking commonalities across cultures and historical periods. Practitioners describe a dissolution of the ordinary subject-object dichotomy, where the sense of a separate self observing the world gives way to pure, undifferentiated awareness. Time perception alters dramatically, with moments stretching into eternity or the entire concept becoming meaningless. Space loses its constricting quality, with some reporting a sense of boundless expansion or interconnectedness with all existence. Perhaps most significantly, those experiencing these states consistently report that ordinary reality is revealed as somehow illusory or superficial, with a more fundamental reality shining through what Buddhist traditions call seeing into the true nature of existence. These experiences are often accompanied by intense emotional tones ranging from ecstatic joy to profound peace, and frequently leave lasting changes in perception and values. What makes these reports philosophically significant is not just their subjective intensity, but the consistent claim that they reveal ontological truth, that reality is in fact as it appears during these unusual states, with our ordinary perception being the distortion. This turns the standard epistemological model on its head. Instead of altered states being departures from normal perception, they might represent returns to a more fundamental mode of awareness that our evolutionary adaptations normally obscure. Modern brain imaging studies of meditators and contemplatives have begun mapping the neural correlates of transcendent experiences. Research shows decreased activity in the default mode network, the brain system associated with self-referential thinking and mind-wandering, along with reduced connectivity between brain regions that normally maintain our sense of separate selfhood. Simultaneously, there's often increased activity in attention networks and areas associated with present-moment awareness. Psychedelic substances that induce similar states appear to work by disrupting normal hierarchical organization in the brain, allowing novel connections between previously segregated neural networks. This entropic brain hypothesis suggests that transcendent experiences may involve a temporary lifting of the brain's normal filtering and predictive processes, allowing a less constrained mode of perception. Intriguingly, these neurological changes parallel the phenomenological reports: less self-focused processing, altered time perception, and a sense of deeper connection or unity. The emerging picture is that our ordinary consciousness involves substantial cognitive filtering, and that certain practices or substances can reduce this filtering, potentially allowing perception of reality less distorted by conceptual frameworks. Philosophers have long debated the epistemic status of mystical experiences. William James identified 4 marks of mystical states: ineffability, they resist full expression in words; noetic quality, they feel revelatory of deep truths; transiency, they can't be sustained indefinitely; and passivity, they can't be summoned by will alone. He argued that while these experiences don't provide discursive knowledge, they offer direct acquaintance with dimensions of reality normally hidden, what Bertrand Russell later called knowledge by acquaintance versus knowledge by description. The perennial philosophy, articulated by thinkers like Aldous Huxley, suggests that diverse mystical traditions point to a common transcendent reality behind their varying cultural interpretations. Constructivists counter that all experiences, including mystical ones, are shaped by prior concepts and expectations. The most radical interpretation comes from mystics themselves, who often claim that in transcendent states, one doesn't gain new knowledge so much as realize the illusory nature of ordinary knowledge, recognizing that the seeker, the seeking, and the sought are ultimately one. This non-dual awareness challenges the very foundations of Western epistemology, suggesting that truth might not be something grasped by the intellect, but realized through the falling away of conceptual mind. Fascinating parallels exist between descriptions of transcendent states and interpretations of quantum physics. The dissolution of subject-object boundaries mirrors quantum entanglement's challenge to classical separability. The timeless quality of mystical experience resonates with physicists' description of time as an emergent property rather than fundamental reality. The interconnectedness reported in transcendent states recalls the holographic principle's suggestion that information about the whole is encoded in each part. Some researchers speculate that certain states of consciousness might allow direct apprehension of quantum phenomena normally obscured by decoherence, that what mystics describe as fundamental reality aligns with how reality behaves at quantum scales before classical observation collapses possibilities into definite states. This doesn't necessarily validate mystical claims, but suggests that the reality glimpsed in transcendent states might share features with the most fundamental levels of physical reality described by quantum physics, a convergence of first-person experience and third-person science that warrants serious philosophical consideration. The central challenge in evaluating transcendent knowledge claims is verification. If these experiences reveal truths beyond ordinary perception, by what criteria can we assess their validity? Mystical traditions have developed various tests: the lasting transformative effects on practitioners, the consistency of descriptions across cultures, and the ability of these insights to resolve philosophical paradoxes that stump ordinary reasoning. Some contemporary researchers propose phenomenological consistency, whether the experiences cohere with other knowledge when carefully examined, and pragmatic efficacy in enhancing well-being and reducing suffering. Yet the very ineffability that characterizes these experiences makes standard verification difficult. We're left with a paradox. The states that might offer the most direct apprehension of reality are precisely those least communicable and hardest to validate intersubjectively. This doesn't necessarily invalidate them. Similar problems haunt quantum physics, where the most fundamental phenomena can only be known through mathematical formalisms and indirect evidence, but it does require developing new epistemological frameworks for evaluating non-ordinary claims to knowledge. From an evolutionary perspective, transcendent states present a puzzle. Why would natural selection preserve brain capacities that seemingly provide no survival advantage and might even be detrimental in immediate life or death situations? Possible explanations include these states being byproducts of other adaptive traits like pattern recognition or social cognition, or representing an exaptation where neural capacities evolved for one purpose are co-opted for another. Some theorists propose that transcendent experiences, while not directly adaptive themselves, emerge from the temporary suspension of normally adaptive but reality-limiting cognitive processes, like lifting evolutionary filters that usually constrain perception to survival-relevant information. This suggests a provocative possibility that what we consider normal consciousness is actually a narrowed, specialized mode optimized for survival, while transcendent states represent a temporary return to a more unconditioned awareness that our ancestors may have experienced more routinely before the development of egoic consciousness. In this view, transcendence isn't an achievement but a remembering, not gaining something new but losing the cognitive constraints that normally limit perception. Modern consciousness research is developing new methods to explore and potentially cultivate transcendent knowledge. Controlled psychedelic studies investigate these substances' potential to occasion mystical-type experiences under laboratory conditions. Advanced meditation research examines how long-term contemplative practice can produce stable trait changes in perception and cognition. Technologies like sensory deprivation or brainwave entrainment attempt to induce altered states non-chemically. These approaches share a common goal: to temporarily suspend or reconfigure ordinary cognitive processing in ways that might allow perception of reality less filtered by our evolved conceptual frameworks. The preliminary results are intriguing. Participants often report insights that align with philosophical and scientific understandings of consciousness and reality, though interpretation remains controversial. What's clear is that human consciousness appears more plastic and capable of more varied states than our ordinary experience suggests, opening possibilities for knowledge acquisition beyond standard sensory and rational modes. The most philosophically challenging question concerns what, if anything, transcendent experiences actually reveal. Three main positions emerge: the perennialist view that diverse mystics access the same fundamental reality behind phenomenological variations, the constructivist position that all experiences are shaped by concepts and expectations, and the eliminativist stance that these are merely unusual brain states with no epistemic significance. A fourth, emerging perspective integrates neuroscience with first-person accounts, that certain practices and substances can indeed reduce the brain's normal filtering and predictive modeling of reality, allowing perception less constrained by evolutionary adaptations, but that what's revealed isn't some absolute thing in itself, but rather the normally hidden processes by which consciousness constructs experience. In this view, transcendent states don't show us reality directly, but show us the constructed nature of our ordinary reality, which is equally valuable philosophically. This approach bridges neuroscience and phenomenology while avoiding strong metaphysical claims. Having explored the possibility that consciousness might, under certain conditions, transcend its ordinary limitations to perceive reality more directly, we're led to consider the ultimate mystery, the nature of consciousness itself. This brings us to our final exploration, the hard problem of consciousness. Why does any of this feel like anything at all? Why isn't the universe just an endless play of unconscious matter and energy? What is the nature of this luminous awareness in which all reality appears? As you settle into the quiet stillness of this final contemplation, we arrive at philosophy's most profound and persistent mystery, the very existence of conscious experience itself. All the paradoxes and puzzles we've explored throughout this series ultimately lead to this fundamental question. Why is the universe not just an endless, unconscious interplay of matter and energy? Why should there be something that it feels like to be you reading these words, the warmth of your hands, the subtle play of emotions, the stream of thoughts flowing through your awareness? This is what philosopher David Chalmers famously termed the hard problem of consciousness, not explaining how the brain processes information or produces behavior, the so-called easy problems, but explaining why and how any of this is accompanied by subjective experience at all. The existence of this inner luminosity, this private cinema of qualia and meaning, stands as the most baffling fact of existence, resisting all attempts at reduction or explanation. As we conclude our journey through mind-bending philosophy, we turn to this deepest of all mysteries, the miracle that against all apparent odds, the universe has awakened and through your eyes and mine has begun to contemplate itself. The hard problem distinguishes itself from the easy problems of consciousness, which are still profoundly difficult scientific challenges, by its resistance to functional or mechanistic explanations. We can understand how the brain integrates information, focuses attention, or forms memories without ever touching the question of why these processes should be accompanied by subjective experience. The hard problem asks why, when electromagnetic impulses traverse neural networks, there is an interior dimension to this activity at all. Why doesn't all this information processing go on in the dark, as it presumably does in computers or other complex systems? This problem becomes stark when we consider philosophical zombies, hypothetical beings identical to humans in every physical respect but lacking conscious experience. The conceivability of such zombies suggests that even a complete physical account of brain function might leave consciousness unexplained. Similarly, the knowledge argument asks whether a scientist who knew every physical fact about color vision but had never experienced color would learn something new upon seeing red for the first time. These thought experiments highlight the explanatory gap between physical processes and phenomenal experience that constitutes the hard problem's core. The hard problem is a modern formulation of the ancient mind-body problem, which has occupied philosophers since antiquity. Dualist traditions from Plato to Descartes posited that mind and matter are fundamentally distinct substances. Materialist responses sought to reduce mind to matter, while idealists reversed this reduction. The 20th century saw various attempts to dissolve or bypass the problem through behaviorism, identity theory, and functionalism, but none adequately explained why certain physical processes should be accompanied by experience. What makes Chalmers' formulation distinctive is its clear separation of the easy problems, explaining cognitive functions, from the hard problem, explaining experience itself. This distinction reveals why previous solutions often seemed unsatisfactory. They addressed how the brain works, but not why its workings are felt. The hard problem thus persists not from lack of trying, but because it points to what may be a fundamental limitation in our current conceptual frameworks for understanding reality. Modern neuroscience has made astonishing progress mapping neural correlates of consciousness, NCCs, specific brain processes that accompany conscious experience. We can identify which regions become active when someone feels pain, sees red, or recalls a memory. We know which neurotransmitters modulate consciousness and how certain anesthetics suppress it. Yet all these discoveries, while valuable, still don't explain why neural activity should be accompanied by experience at all. The explanatory gap becomes particularly apparent when considering how subjective qualities, qualia, like the taste of coffee or the smell of rain bear no resemblance to the neural activity underlying them. There's no obvious reason why a particular pattern of firing neurons should feel like anything, let alone why it should feel the specific way it does. This suggests that while neuroscience can reveal the physical substrates of consciousness, it may need fundamentally new concepts to explain how and why these substrates give rise to experience. Philosophers have proposed various responses to the hard problem, falling into several broad categories. Dualist approaches maintain that consciousness is fundamentally non-physical. Substance dualism posits two distinct substances, mental and material, while property dualism suggests that experience is an irreducible property that emerges from certain physical systems. These approaches face the challenge of explaining how non-physical consciousness interacts with the physical world. Physicalist/reductionist views argue that consciousness is identical to or reducible to physical processes. Some propose that we simply lack the concepts to understand this reduction, while others suggest consciousness is a fundamental property of matter that only becomes apparent in complex systems. These views struggle to explain why the reduction should involve experience at all. Panpsychism offers the radical view that some rudimentary form of experience exists at all levels of reality, with human consciousness representing a complex organization of these fundamental experiential properties. This avoids the hard problem's sudden emergence but faces challenges explaining how micro-experiences combine into macro-consciousness. Eliminativism and illusionism propose that phenomenal consciousness doesn't exist as we think it does, that our sense of rich inner experience is itself a kind of illusion created by cognitive processes. This counterintuitive view suggests the hard problem arises from mistaken intuitions about experience. Each approach has strengths and weaknesses, but none has achieved consensus, indicating the depth of the challenge the hard problem presents. Some theorists have turned to quantum physics for insights into the hard problem. The measurement problem in quantum mechanics, why observation collapses quantum superpositions into definite states, has led some to suggest consciousness plays a role in reality's fundamental workings. The von Neumann-Wigner interpretation proposes that consciousness causes the collapse of the wave function, while other approaches explore how quantum processes in microtubules within neurons might relate to experience. These ideas remain controversial, with most physicists maintaining that quantum effects are unlikely to be significant in the warm, wet environment of the brain. However, they represent creative attempts to bridge the gap between physical theory and phenomenal experience, suggesting that solving the hard problem might require rethinking physics as much as neuroscience. Several major theories attempt to explain consciousness while addressing the hard problem. Integrated information theory, IIT, proposes that consciousness corresponds to a system's capacity to integrate information, measured as phi. It suggests that any system with sufficient phi would be conscious, potentially including non-biological entities. IIT takes consciousness as fundamental rather than emergent. Global workspace theory, GWT, views consciousness as arising from information sharing across specialized brain systems via a global workspace. While explaining cognitive access, it doesn't fully address why such sharing should be accompanied by experience. Higher-order thought (HOT) theories suggest that conscious states are mental states we're aware of having. These address metaconsciousness but still leave the base level of experience unexplained. Predictive processing approaches frame perception as the brain's predictions about sensory input. While illuminating perception's constructed nature, they don't inherently explain the presence of experience. Each theory offers valuable insights while facing challenges in fully resolving the hard problem, suggesting that a complete theory might need to integrate multiple perspectives or develop fundamentally new concepts. The hard problem's persistence has profound implications across multiple domains. In neuroscience, it suggests that explaining brain function may not suffice to explain experience, requiring new theoretical approaches that bridge the physical and phenomenal. For artificial intelligence, it raises questions about whether sufficiently complex information processing would necessarily produce consciousness, and how we could know if it did. In philosophy of mind, it challenges standard physicalist assumptions and forces reconsideration of reality's fundamental nature. Ethically, it affects how we treat entities, animals, potential AI systems, that might possess consciousness, given our difficulty defining or detecting it objectively. The hard problem thus isn't just an academic puzzle but a fundamental challenge affecting how we understand ourselves and our place in the universe. As consciousness research progresses, several promising directions may help address the hard problem. Developments in neuroscience may reveal more about how specific neural architectures give rise to different aspects of experience, potentially identifying necessary conditions for consciousness. Advances in artificial intelligence could create systems that claim consciousness, forcing us to refine our understanding and potentially creating new models of experience. Interdisciplinary approaches combining neuroscience, physics, and philosophy may generate new conceptual frameworks that better bridge the explanatory gap. Contemplative traditions' systematic investigation of subjective experience could provide data about consciousness's varieties and potential transformations. While the hard problem may never be solved, in conventional terms, these approaches might lead to a deeper understanding that transforms how we frame the question itself. As our journey through these philosophical paradoxes concludes, we return to where we began, with the miracle of consciousness itself, the ground in which all these mysteries arise. The hard problem stands as both a profound challenge and an invitation to wonder at the fact that the universe has somehow given rise to beings that can experience, reflect, and puzzle over their own existence. In this final quiet moment before sleep, as the boundaries between self and world soften, you might sense what all these paradoxes point toward, that consciousness is not just a problem to be solved, but the fundamental mystery at the heart of reality, the luminous space in which all questions and answers appear. Thank you for joining me on this journey through mind-bending philosophy. If these ideas have sparked your curiosity, please share your thoughts in the comments below. What paradox resonated most deeply with you? Don't forget to like and subscribe for more content that explores life's deepest questions. As we part ways, remember that the greatest mystery is not out there in the stars, but right here in the awareness reading these words. Good night, and may your dreams be filled with wonder.